now. Okay, so let's get started. I think while people is joining, we can start now. So welcome everyone to our first ARCU workshop on initial activities for the collaborative platform for CAN-ASM, CP4C. Well, I'm Daniela Boden, the manager of the Center for Climate Science and Engineering, which is a research and education center within the Civil and Mineral Engineering Department at the University of Toronto, where Paul Kushner is an executive member as well. In regard to the CP4C project, I am the project manager. My professional background is civil engineering with experience in drinking water and sewage systems projects, and with a master in engineering and resilience infrastructure and sustainability in cities, who now is learning about the world of climate modeling and analysis. So before we start with today's agenda, I would like to give a quick introduction to the collaborative platform for CAN-ASM. The CP4C is a research platform that will enable the Canadian research community to work collaboratively with the Environment and Climate Change Canada's Earth System Model. The CP4C initiative was launched under the auspices of the CMOS Special Interest Group on ARCU. It is important to know that the CP4C is not an initiative of the ECCC, nor any given university. On the contrary, it's an independent project which draws on seed funding from the ECCC, compute resources from Compute Canada Alliance, and in-kind time support. So the CP4C goals are categorized as overreaching, collaborative, and technical. So the overreaching goal is to enhance climate science information delivered to Canadians. The collaborative goal is to enable collaborative partnership with ECCC for the Canadian research community to use a collaboratively developed CAN-ASM. And the technical goal is to develop a production and analysis capacity for CAN-ASM, ported to high-performance computed platforms, extramural to Government of Canada computational facilities. So moving on to the workshop schedule. As all know, this is a two-day workshop, and for today we will provide an overview of the CP4C project and updates on CAN-ASM. We will have 8 presentations. Each speaker will have 50 minutes to conduct their presentation and 5 minutes to respond to questions. We will have 2 breaks in the middle of the presentation, and at the end of the session, Paul will moderate the final discussion and some reflections and the plan for tomorrow. So for tomorrow, we will start at 1 p.m. Eastern Time, and we will host 2 panel sessions. The first panel will focus on the status and development plans for CAN-ASM. The moderator will be Paul Kushner, and the panelists for this session will be Vivek Arora, Jason Cole, Jamping Lee, Paul Myers, Ivy Tan, Neil Swart. And for the second panel, it will focus on CP4C, Science Application and Collaborative Environment, and it will be moderated by Neil Swart. And the panelists for this session will be Joe Melton, Andrew Shaw, Hansi Sin, Clint Seinen, Jack Virgin, and John Sinoka. So briefly, the purpose and objectives of this workshop are to introduce and report on initial steps to develop the CP4C, report on the results of CP4C activities supported by the seed funding from the ECCC between November 2021 and March 2022, This workshop represents the first activity for the Compute Canada Alliance Research Platforms and Portals project and will be included in the annual report to Compute Canada Alliance. Just to remind you, we will have 2 days workshop. Day 1, I mean today, will focus on an overview of the CP4C project and updates on CanASM. And tomorrow, we'll focus on discussion of CanASM and activities and policies for the CP4C community. So as an additional note, before we start, we thank University of Toronto students, Alexander Audet, Haruki Harisawa, and Jack Won for acting as our reporters for the meeting. Also, we invite you to ask questions and make comments at the Google Doc posted right now. I will just add it in the chat so everyone can see it. And please feel free to ask questions through the chat or verbally. We will have 5 minutes at the end of each presentation to address those questions. Reported notes, recording, and workshop material will be posted following the meeting. And finally, we request the speakers to please introduce yourself before your presentation and allow enough time for questions. So now I will pass it over to Paul Kushner, who will talk about the CP4C project overview. So thanks, everyone.
Thank you very much, Daniela. So I want to continue and let me find my PowerPoint presentation. Now, if I go to full screen on that, there's always the moment of fear, right? Will it actually work? Did it work or no? No, you see my slide. You see my slides, yes, right?
Exactly. And your notes as well. Yes.
See my notes. Okay, so I'm gonna. I will cancel that share. I have done this before, but it's always an adventure. Okay, I'll try one more time. Share screen. And one. Oh, I see. Okay. Let's try that. Does that work? Can you see
yes.
my slide? No, but not my notes. Okay, great. All right. So my purpose here, first of all, is to welcome everyone and thank you for coming. We have excellent attendance. I think we're looking at just over 40 participants, and that's great. And so today I'll be giving you an overview of the project. I think Danielle has given a very nice summary. And I'll touch on some of the same themes, but I also wanted to give some background on how we've arrived here, and then hopefully get some discussion going right away. So first of all, just to acknowledge those on this slide, that I would call this the CP4C team currently, and so there's Neil Swart and Jack Wong, Haruki Hirasawa, Clint Synan, and Daniela. And you'll hear from all of them in one way or another over the next couple of days. And I just wanted to acknowledge all their help and great activity in this. Okay, so just to start with some background. So actually, I don't know if you remember, but we met about a year ago, just over a year ago, March 11th of 2021. And this was the leadoff slide, okay? And we had a larger discussion about the overall interest in developing and working with a collaborative version of CanASM. So this was an ARCU workshop from about a year ago. Everything was recorded, and we had a lot of input from many members of academia and Environment and Climate Change Canada, both inside and outside the Climate Research Division. So if you remember, we had a review of a survey that we undertook earlier in the year. And then we also talked about developments going on with CanASM, and had some panel discussions about possible projects we could undertake. So it was pretty open-ended. But one of the commitments we made at the end of this was to have a follow-on activity, and that's what's taking place today. Okay, so I want to remind you of this survey that we undertook. So I think we had about 45 respondents in that survey, maybe 50. And of those respondents, 30 of them were faculty at Canadian universities who, who lead research groups. And so potentially could be bringing a lot of new trainees and new researchers into the fold as we work together on a new version of CAN-ESM. And I would say that from this community survey and from our discussions, I would characterize the interest as healthy. And I'd say fairly realistic, reasonable expectations for what was on offer in developing a collaborative CAN-ESM type activity and project. So the key conclusions we came to were that the collaborative version of CAN-ESM, it's a technical project, but it's also a tool for collaboration. And there was a real desire from everybody who answered these collaborations to enhance the survey rather, to enhance collaboration with scientists at Environment and Climate Change Canada, and working with CAN-ESM was seen as a really good mechanism for doing that. And the interest in kind of the investments that needed to be made and the concerns there were really around the long-term commitment from ECCC to maintain some version of CAN-ESM that is really collaborative. In other words, people were prepared to invest some time, their own research time outside ECCC, as long as there was a long-term view that there would be a collaborative CAN-ESM around for several years, and supported and actually runnable, and was something we could do work with. And so part of that is, of course, having good documentation, support meetings like we're having today. But there were a few people who had concerns about the lack of direct technical support. I think that has to be acknowledged. But overall, that was relatively few people, and there's a recognition that for community modeling projects, often there isn't direct technical support, but you can still get a lot done with the community involved. I also want to point out that our survey and the group that was assembled last year was perhaps a little broader. We also asked about interest in other ECCC models, or the families of models that are developed within ECCC, which of course cross different division boundaries and different applications. So I just want to make sure that people remember this, that there was quite a desire to have enhanced access to other ECCC models, regional models, forecast models, those kinds. So I don't want to leave that aside entirely, but certainly the focus of today is on CAN-ESM, acknowledging that there is really also a healthy interest in exploring other modeling frameworks at ECCC. So a point that was kind of implicit in everything that we talked about last year was that these collaborations, hopefully, all the way through will be two-way, and that it's definitely, this is maybe more my view, but I think it came out through the discussions that this collaboration should be also in ECC's interests, and I think it will be as we go forward. We'll see that. Okay, so I hope all that makes sense. So that was last year. What's happened since? So one of the things we committed to at the workshop last year was to go ahead and propose an ask for some resources to find both computational and funding support for this effort. So I think it was in early summer last year, I sent out an email asking to the ARCU email list, asking for expressions of interest to contribute to a research portals and platforms proposal to Compute Canada, which is now called the Alliance. We got some interest and put together a proposal. And then and I'll talk about that in a little bit, but based on that response, then within that group, I also asked whether others would be interested in joining on a funding proposal to NSERC Alliance mission in partnership with ECCC. So we submitted some proposals. So we sent a proposal to Compute Canada Alliance for this RPP, and I'm pleased to report this was successful. We obtained a pretty good fraction of the compute and cloud compute resources we asked for. Also, Neil, who has been the PI of a Compute Canada resource for research groups, proposal, and he got that renewed under the so-called fast track, which it's a pretty straightforward process to get that renewed, and that was renewed on the CEDAR platform. And also with encouragement from Neil and CCCMA, I submitted a proposal for some grants and contributions funding for ECCC based on this project on CP4C. And yes, that was also successful, and that's what actually supported us over the last few months, because and that funding is ended as of March 31st. And sadly, several of us put together what I think was a very good. Of course, one always likes one's own proposals, I guess, but this was, I really thought we made a very strong case. And disappointingly, our NSERC Alliance mission proposal was not funded. We didn't get much feedback, but the ideas are still there, and the ideas are carried forward in what we'll be talking about today. So unfortunately, we don't have the core funding we were hoping for, but we definitely made a commitment to report on progress at this point to ECCC and to Compute Canada, and so that's what we're doing today. So what have we been up to? You'll hear more as we go on. From November to March. So November of last year is when we had some GNC funding come in to the U of T. And we put together this group with support, including support for Daniela, Jack, Haruki, and one other person who I'll mention a little later. And as a working group with people also providing lots of in-kind time support, Neil and those on the slide I mentioned at the beginning, all started to meet frequently, about weekly, to get to work on the technical work here. We spent a lot of time planning for this workshop, and we've now submitted an expression of interest for renewal for funding for CP4C as a grants and contributions. And so that's all we've done. We've expressed interest in going forward, and we'll have to see what ECCC, how ECCC responds. Okay, so what is the CP4C? So Daniela has given you a good overview. I'll try not to repeat what's been said already. It's a research platform which is envisioned within Compute Canada resources in a certain format. But basically, it's the set of tools we need to carry out research in collaboration with ECCC using CANISM. And the idea is to enable, to enhance, to lower barriers to collaboration, and to pursue ECCC's stated interest of collaborative development with CANISM. Specifically, it's a technical project, so it's what we're developing is a technical workflow to port the code easily from one platform to another, to run the code, do production runs, to record and document the runs that are done, and to analyze and do science with CANISM simulations. There's a two-way flow of developing capacity, so developing new capabilities within CANISM from this collaborative community outside of ECCC. We want to set up some scientific research examples so people can get started on their own research with very well documented examples, templates for working on with CANISM, and there's also within the proposal that we had, there are modest compute resources. So what we want to do is, what we're already doing actually, is testing the ports of CANISM. We actually want to carry out limited production simulations, and also systematically document through database capabilities and some of the cloud computing, document and have tools to quickly analyze the simulations. So there's kind of a mix of technical goals here. But overall, it's to recognize that whenever you get involved in Earth system modeling, you're talking about codes that have 1 million lines at the core, but also lots and lots and lots of scripts and things you need to do to vet and analyze these runs. So we want to make that easier, more straightforward than it has been. Okay, so in the proposal that I actually shared, Daniela shared with you the proposal, and we had some other proposals that some of these tasks are drawn from. So the initial goals of the CP4C project over a 3-year period, I could say that's begun, say as of November last year, is that we would basically split into developing the platform and then using CANISM. That's kind of the two overarching themes. And within that, there are several tasks. First of all, to create a build from scratch or bare metal port of CANISM 5, the current version, to develop a production analysis workflow with something called IMSI, which will be described a little later, to carry out some production simulations, which would be basically to reproduce the so-called deck of CMIP, which is a kind of standard set of simulations that each modeling center produces. ECCC has produced this within its own compute environment, and we want to reproduce some of those same runs outside of ECCC on Compute Canada Alliance platforms. To test the ASM workflow and refine that workflow as we go along. And then as far as applications, the first thing we thought we should do is train ourselves to use CP4C. So whoever was going to be, working on CAN-ESM, whoever was working within CP4C needs to get to know the model and how to work with it, because there aren't many of us outside of ECCC, including myself, who really know the model well. So this was one of the first things to do, is sort of train ourselves with available documentation and lots of help from Neil and Clint and so on. And then we could go into a position of training the larger community. So providing good documentation, getting feedback from the community, and then we could start collaborating. So collaborating on technical development and then also on scientific applications. So in the next slide, I'm going to show you the same information, but sort of showing you where we are in terms of the status after a few months of work. So in green is what I would say we've accomplished, which you'll see is one thing, which is, I think, really not bad. And then in progress in yellow and things that are planned still haven't been done yet are in red. Okay, so Jack is going to tell you about his experience porting CAN-ESM using the workflow software developed by Neil and Clint called IMSI. You can see that there's lots we haven't started yet. And this is where, the additional need for support and time, of course, comes in. But I think there are good prospects for doing these other things. So when red doesn't mean stop here, it just means it hasn't started yet. We've begun to become familiar how to run the model, right? So I would say that's fair to say that that's in progress. And also there's some technical work going on in terms of building capacity within CAN-ESM to check reproducibility of a ported version of the code. So Haruki will give a presentation later today on the ensemble consistency test, which is one example of the kind of quality control you need to do, or quality assurance you need to do, as you move an Earth system model from one platform to another. So I'll let him tell you about that. So we're still not at the stage of actually doing science with this framework, but I think there's good prospects for that, and we'll certainly have a chance to talk about that tomorrow. So just to tell you about the resources, these are resources that we are using and that we're going to start inviting you to work with. So the work that we've done, we've got the chunk of funding I mentioned, and we're going to continue this into the summer to actually create a wiki and a website. Hopefully we'll be able to provide some useful resources for everybody. And then as I mentioned already, we're hoping for this will be renewed. The current team is the co-authors. Okay, so that's this group here that I mentioned. So Neil, Jack, Haruki, Clint, Daniela. So we're all there supporting this effort. If you'd like to join in on this effort, we do actually have a couple of other students who've been listening in, and if you'd like to join in, we're going to continue our work through the summer. So at a certain level. I'd like to hear from you if you're interested in really getting into this early on. And there's a working and optimized version of CAN-ESM that now exists on SciNet. This is kind of the next step into the containerized version of the code that Neil Swart has developed over the last couple of years. This is built from scratch. It's great. It runs well. The output right now, I would say, is of limited scientific utility, because mainly it's the I/O has not been fully kind of converted into the worldwide standard for output from Earth system models. So there is output, and there's but the thing is that in terms of the real easy to use output that you might expect from Earth system modeling, right now, it's mainly confined to surface fields, and then there's lots of binary files that would require a lot more work to use. So I would say at this point we have output, and we can do it for some limited testing and even look at the fields, and that's great. But there still needs to be some work, and so what I expect is that we should have a port with a more useful diagnostic output and production capability sometime by the end of the summer. This is actually partially contingent on what's going on inside ECCC as they move to new compute platforms. And Neil, you're welcome to comment if I have gotten anything wrong here, or any of you from CCCMA. And once that's ready, I think it will be in a good position to hold a tutorial, which will be, exploratory. We'll see how it works, but I'd like to see that happen sometime in the summer, if for no other reason that I get incredibly busy in the fall with teaching, and so selfishly I'd like to have it happen before I start my fall semester. So that we've talked about that, and I think that'll go ahead in some form. All right. In terms of this allocation, so we have about 100 core years, so a couple nodes, sort of 2 to 5 node simulations we can do from both the Neil's RRG application and our RPP allocation. And we also have cloud resources that we won't talk about so much today, but those will be useful for doing kind of the diagnostic analysis that was outlined in the proposal. And we're preparing some initial tutorial materials and CAN-ESM documentation. There's certainly documentation Neil has already prepared out there for CAN-ESM, but actually like instructions on how to run things and all that's in prep. I also wanted to point out, this is the header from the CAN-ESM proposal. And there's a bunch of people listed here, and all of these PIs listed as co-PIs on this proposal. Everybody here who's in that list, who's online today, you actually have access to this allocation, right? So right now you can actually use this allocation. And it's a rolling allocation, so it does make sense to take advantage of it. That being said, we haven't told you, how to go ahead and do this, but I'll certainly, I want you to be aware of that. Okay, so just to say, this is like a brief slide just to conclude is, what we're trying to do here is build the collaborative community using this new infrastructure. And so I'm just really interested in hearing your ideas and thoughts as we proceed through the workshop, bearing in mind our constraints, the lack of funding. This is a relatively small project within, a larger framework that ECCC is working in. So there's only so much we can actually control here, but I think your ideas, your technical ideas, and your science, your organizational ideas are very, very welcome. And so I'm looking forward to seeing these talks, which will be a mix of recent work on what's going on with CAN-ESM at CCCMA and the initial work for CP4C. So have I left any time for questions? Probably not. Is there maybe any quick questions? And I also, if you want to look, if you're asking questions in the document that Daniela linked, that would be, so that's still in the chat. For those who joined late, you can, I'll repeat it anyway.
We have a question from Paul Myers.
Oops, don't click that Airbnb link. That's not the one I meant to send, unless you want to stay in Little Italy for the month of May. Okay. Okay.
Paul Myers.
Yes, Paul, go ahead.
Yeah.
I don't want to spend a lot of time, but just when you made the comment about trying to get, the output on Niagara assembled into, I'm assuming when you meant by a usable form like netCDF and binary, I just want to mention, we've spent a lot of effort working to get those conversions working using NEMO, and some of what we've learned might be very useful for the rest of CAN-ESM. So maybe that's just for offline. I just wanted to mention that.
Yeah. Okay. Noted. So yeah, right. The code is a coupling of CAN-AM and the Canadian land modeling, but also with the NEMO Ocean model, which has a separate community, and so there is and we might get more discussion of that a little later. But noted, Paul. Thanks very much. Any other questions or comments?
I can see any other question or comments.
Okay, yeah.
Okay,
So I apologize for breaking the format right away by not allowing enough time for discussion. I didn't think it would take that long. All right, so let's, yeah, I'll stop sharing.
We'll welcome Neil Swart from ECCC, who will talk about the collaborative CAN-ASM. Neil, let me know if you have issues to share your screen. No, here we go. We can see it now.
Okay, fantastic. Okay, well, yeah, hi everyone, nice to be here again. So as Paul mentioned, we did meet about a year ago. I gave a talk at that meeting, which was discussing what we had done so far on this collaborative CAN-ASM project. So today I just want to touch on a few highlights of that, but talk about how CAN-ASM itself has evolved and what we plan to do kind of internally to CCCMA, and then also the progress that we've made on some of these challenges regarding the collaboration. Okay, so that's basically what I want to tell you about today. And so last talk, we discussed how CAN-ASM has this pedigree going back about 40 years. And certainly some of the components within CAN-ASM have been collaboratively developed. But because of more strict computing policies, that has actually tapered off over recent years. So really this activity is to try and reinvigorate that collaborative development of the model code. But in addition to the development of the model, there's also participation in these major international projects, and particularly, for example, participation in these CMIP exercises has led to the creation of a lot of public data that there has been a lot of use in the community of, and collaborative analysis between scientists within ECC and external to ECC. So there are these kind of like two formats, the more development side of the model, and then also the analysis of the output. I also mentioned last time essentially what's the ECCC commitment here, which is articulated in the CCCMA strategic plan. And that does seek to foster increased collaboration with the broader community. And there was this kind of virtuous cycle imagined here, where by standardizing the modeling framework and adopting these kind of common coding standards, we would hope to facilitate collaborative development and analysis of the model that would basically improve the human resource capacity that was available, and this would be this kind of virtuous cycle that carried on. So the idea here really was to enable collaboration through embracing standards and good documentation and that kind of thing. The idea was not to try and create CESM of the North, as Paul likes to say. So it's a different model that we're envisaging compared to some other community models, but maybe it's a little bit more like what the NEMO community does, or what, say, people do with GFDL models, perhaps. So what I want to just mention here quickly is what's happened since CAN-ASM 5.0. That's the model version that was used in CMIP 6, and we've gone through a full development cycle in CCCMA, and today our production model is CAN-ASM 5.1. So CAN-ASM 5.1 is basically very similar to CAN-ASM 5.0 in a physical sense, but it has really widespread syntax and structural changes. So there were about 25 merge requests, about 450 commits that went into forming CAN-ASM 5.1. And the major changes really occurred in CAN-AM, where the whole code base was updated to Fortran 90 syntax from the old F77 or even F66 in some places. So that was really part of this modernization exercise that we've been talking about. There was a major update to the way that arrays were handled in the model, again, facilitating kind of these interactions. We introduced this full compatibility between the GEM dynamical core and the spectral dynamical core. So CCCMA physics can plug into either dynamical core basically seamlessly. It's literally exactly the same physics package, exactly the same code. So that's really important, as we'll see in a second. There's a bunch of quality of life improvements and a few bug fixes. In terms of actual physics changes, really the only change was the mapping going through the coupler was changed to improve the fields that the ocean was receiving. And we had updated a few of the kind of boundary condition files, but mostly the changes in this model version are technical as opposed to physical. One really important activity that happened was the spin up, just the beginnings of the spin up of a much more objective tuning exercise for the model. And that achieved two things. The first thing that it achieved was elimination of these dusk spikes and sudden stratospheric warmings that were identified in the CMIP 6 output that were quite unrealistic. So those issues were resolved through basically tuning these hybridization parameters that relate to the spectral transport and conservation. Perhaps more interesting, though, is that John Snoka and Slava Karin have really started to spin up a much more comprehensive and detailed objective tuning exercise for the model. And just one of the first applications of that exercise was to ask, can a model with exactly the same physics produce a lower climate sensitivity just by tuning the parameters? And this was motivated by the fact that CANISM 5.0 was the highest climate sensitivity model in CMIP 6. And so we wanted to see if just parameter adjustments could have changed that, and that was achieved. So I'm just going to talk about that. So these are these DEC simulations that Paul was referring to, the standard DEC, PI control, historical. These labels are the wrong way around. This is 4 times CO2, and this is 1%. I thought I fixed that. Okay, but anyway, these are the DEC simulations. This is global mean screen temperature, and this is from the CMIP 6 contribution. The CANISM 5.1, the default version of this, has basically exactly the same climate as CANISM 5.0, but again, all these technical changes within it. And then when we apply this tuning, so what we call the physics 2 version of CANISM 5.1, you can see that there's much less warming in these idealized increase in CO2 scenarios. So that corresponds to a decrease in the climate sensitivity by about a Kelvin. So that it's still a high climate sensitivity. It's still about 4.6 Kelvin for a CO2 doubling, but it's significantly lower than it was in CANISM 5.0 or in the default tuning of 5.1. So as we go forward, this objective tuning exercise is going to produce a range of models that we can select from that might have different properties that are all equally valid. They all use the same physics, just different parameter tunings. Okay, so that's where we are, and where we're going is from CANISM 5 to CANISM 6. And the major changes that are envisaged is changing out the spectral dynamical core to the GEM dynamical core, retaining the same CCCMA climate physics. And this is associated with about an expected tripling in the resolution of the atmospheric model. So that's a major improvement there. On the ocean side, a change from NEMO 3.4 to NEMO 4, and hopefully, at least for some experiments, we hope to run the 1/4 degree, so about a quadrupling of the resolution there. There'll be an updated land surface and land biogeochemistry, and there'll also be changes in the coupling infrastructure. Another important change is moving from this legacy CCMA environment and tools to more a collaborative environment and tools. So we've got a lot of work items that are planned to kind of complete before we can do testing and enter into the CMIP 7 exercise. So that we've got a really busy schedule at CCCMA, but this is basically what we have on the cards for the next couple of years. Okay, so that's the model as we kind of develop it, but what about this collaboration? So I'm just going to reflect really quickly on some of the things that we talked about last time. So I'd outlined 10 elements that I thought we needed to achieve a collaborative CANISM. Some of those were a complete open source code base, which we have. And I spoke about this publicly available open source code. One of them was a reproducible runtime environment, and we spoke about this container that can be used on commercial cloud or on HPC systems, and that we could run the model in this. We talked about having some documentation to support this usage. We talked about testing on Google Cloud Platform and on Compute Canada. And we mentioned that when we run on Compute Canada, the efficiency of the model measured in core hours per simulated year was basically the same as what we had internally in our CP4C HPC. But the absolute throughput was quite low because we were only using one node. So Jack will talk later about work where we've expanded to multiple nodes and really optimized the performance. So that's a big gain that we've made. The other thing that I talked about was testing the climate between the runs on Compute Canada and our internal runs, and showing that the climate was statistically indistinguishable. And Haruki is going to present a more objective way of doing this comparison too. Okay, so we had these 10 elements of collaborative CANISM, and there were some of them that were kind of achieved, and then there were some of them where we identified challenges, and particularly this portable and standards compliant code, setting up the experiment configuration and forcing the usable input output. This is where we really talked about the challenge is more on the CAN-AM side, where we have the CCCMA format that most people don't know how to work with. And so how do we implement this really complicated post-processing pipeline to produce the more standardized CMIP and etcdf output that people might be used to? And then there was also some questions about how we organize this activity in terms of the philosophy. So what we've done over that last year then is created this new system for configuring the model. And so essentially this allows us to configure the model on dozens of different platforms, or compute platforms, over different model configurations and over literally hundreds of experiments. So we've basically got this much more portable way of moving the model around in the configuration of the platform and experiment configuration. So this is MZ that's basically in beta testing now. So using MZ, basically I ported KNESM 5.0 to Niagara. As Paul said, this is a bare metal port, so not using the container. It's not necessarily better or more efficient. It's just provides a little bit more flexibility. And as we will hear, there's some students that have been able to run hundreds of years of simulation using this setup. So it's proof that other people can independently use it, which I think is good. So the next major thing we did was develop this new sequencing capacity using the portable community tool called Silk. So Silk is a community sequencer used by a lot of climate research groups around the world. And basically we've implemented this whole workflow that we have into Silk, and we're in alpha testing of that now. But basically this is going to make a real big difference in terms of the ability to bring this whole complicated diagnostic pipeline to the Compute Canada systems or to any system, as opposed to struggling to support that. So yeah, the basically progress on these issues for CanAM, we really improved by doing that syntax update. CanDiag is honestly still a challenge. The experiment configuration for forcing has been brought forward by MZ. The usable input-output file diagnostic capacity, we're hoping that MZ and Silk together are basically going to solve this, because we will be getting the final CMIP standard NetCDF out by the time we implement this whole pipeline. And then in terms of the collaboration philosophy and support, really the CP4C exercise, I think, is taking that on, and particularly in the panel discussions tomorrow, I think we're going to have some discussion about how to organize this activity. So I think that's where this will be addressed. So yeah, that's it. Thank you.
Thank you, Neil. We have a question in our chat from Philippe Lucas. What is the time horizon when KNESM 6 using GEM will be ready and available?
Yes, so I mean, right now what we have is the spectral version of the model that's available. So ultimately the plan is to make the GEM version of the model available, but we're not even using GEM internally. So this is GEM is not used in the ESM internally. It's just being tested on the atmosphere only side. So it's going to take several years before we fully integrate GEM into KNESM. And then there's a whole bunch of work in terms of making GEM portable. So basically that's going to take years, definitely at least years, I would anticipate. So it's not a short time horizon for that, but we do intend to maintain this collaborative ability after making the move to GEM.
Great, thanks. Vivek has his hand raised. Vivek, you can unmute yourself. I think we cannot hear you. No, not yet.
Now you have to unmute, I think. Yeah.
No, we cannot hear you. Or he will rejoin maybe. Let me see if we have something in our file. No. G has the raise hand. G, you can unmute yourself.
Do you hear me okay?
Yes.
Okay, I have a science question, if I may, and maybe a comment question about the program. Science question is about the perturbed physics run that you mentioned that led to different climate sensitivity. Can you explicate that a bit? What particular physical parameters are found to I find to be important. And my programmatic question is, I noticed GEM is mentioned. I was wondering whether this initiative or can this initiative include porting GEM to the Compute Canada platforms? Thank you.
Okay, so I'm going to maybe answer the second one first, and then I'm going to defer on the first one. On the second one, when CCCMA integrates GEM into CANISM, and if that works, because we don't 100% know that will work yet, there's a lot of challenges ahead about coupling that into the ESM. If and when we get that working, then ultimately our plan will be to make that available, but that will be GEM using CCCMA physics within CANISM. It's not our mandate or within our wheelhouse to make the numerical weather prediction version of GEM. So GEM using RPN physics, we don't have, it's not our place to interact with the community on that. So I can't speak to that. I can only speak for our use of GEM. But so yeah, I'll just leave it there for that one. For the first question, it has to do with the parameters in the convection scheme, I believe, but I'm just going to defer to John, who I see is on video, because he will give you a more accurate answer than I would.
Yeah, so we've been working for a number of years on a new approach to tuning the model, which is a black art in any climate lab. And all I'll say is the approach is based on a technique by Daniel Williamson at the University of Exeter. He's a statistician, and it's called history matching. And it involves taking observations with uncertainties and trying to ask the question, what physical parameters might you select to finalize a model that fit within those uncertainties? And so it's kind of another paradigm compared to an optimization problem to find the best parameters. It's to find sets of parameters that you can say, I can't say this is any better than another set because all of them produce models that fit within OBS uncertainty. So that's kind of the basic approach for this automatic tuning.
Yeah, and in terms of the specific parameter, I can send it to you, but there's a specific parameter which I think relates to the shallow convection rate that actually is the thing that, it's the one parameter that really changes that climate sensitivity dial. I think that's correct, John.
I mean, it's well known that the entrainment of the shallow convection in other groups has been used to tune climate sensitivity, but our entrainment rate is a prognostic quantity, not a tunable quantity. It's hard to, it's hard to say any one because this is a collection of free parameters. You have the free parameters and all of them have different values. So it would take some analysis to sort of break it down to say specifically any one of them led to it. But I think the idea is that convection plays a pretty big role, particularly the shallow. Yeah.
Thank you.
Thank you, Guy, for your question. Vivek is here. Yeah, Vivek.
Can you hear me now?
Yes, we can hear you.
Okay. Yeah, I have to disconnect and connect again. Thanks, Neil. So at CCCMA, Neil and Clint, of course, lead this effort, and as developers of CANISM, we have a hard time keeping up with the changes they make. So Neil is very good, and Clint they are good in providing us lessons on how to use this. They keep providing us an update, but we are a team of reasonably sized people, 20 or 30 people working on model development. So my question to Neil and Paul is, if the system changes under the hood so quickly, how do we expect Paul and his team to keep up with the changes that happen so fast? I mean, so that's it's a more high level technical kind of question.
I don't know if there's a good answer to it, but my hope is that we've had to check with CCCMA, for context for people, had a period of about 30 to 40 years where no changes were made at all, basically in the infrastructure. That accumulated a massive technical debt, and we've had to climb out of this debt hole, which has led to this very sharp learning curve as a lot of things have changed. My hope is that once we get over that and onto some of these new systems, we'll be on a plateau with a much more gentle rise where there'll always be some continuous change. It's never going to be perfectly stable, but the rate of change is hopefully going to slow down after we've kind of relieved some of the big burdens with technical debts that we had. So that's what I hope. But yeah, at the moment, as we kind of move towards, say, like Silk, MZ, all this stuff, internally and externally, The reality is just that, yes, we have to change things in order to get them working. But the idea is that we will have exactly the same system internally and externally. So that's the ultimate goal, and we're not that far away from it. So I'm kind of excited about that.
Right.
And it's going to be better. It's going to be better for everyone.
Right, and so this is a lot of work for you that you have to support not only people inside CCCMA, but this community as well. So yeah, I just want to acknowledge that. So thank you.
Yeah, and that's where I think that being the identical system and everyone just being able to follow the same instructions is key. So we're not providing NCAR type support. That was one of the statements.
Okay, thank you.
I just want to add, because I think it's an important question, which we'll come back to, and just to say that, with a lot of us have experience. I think everybody on the call here today has experience using models that change rapidly and deciding when to adopt updates, right? And there, for downstream users of downstream climate models may be doing minor changes to those models that they will want a stable version to work with, but that's already on offer with CAN-ESM 5, right? That's something that is going to be around for a while, and I think scientifically supported. Others are really interested in the latest and greatest, right? And they'll be impatient and champing at the bit for whatever's coming. And I don't think it's clear that there can't be an obligation to support all those users and all their possible needs, but it's more to make it clear like what the reasonable expectations are. And last year, I think I got a sense that there were reasonable expectations, right? The many people using Earth system modeling in Canada, using platforms outside of Canada, like mainly NCAR, but not exclusively the CSM, we're kind of used to that. We're used to a certain level of deciding when to jump in, when we need to interact with the latest version, and so on. So yeah, so it's a work in progress, though. There's no simple answer. I think we should move on. Yeah. I'd just like to encourage everybody to use that document. If you have things that you want to, use the document that I pointed to, the Google Doc that Danielle and I pointed to for more comments. It'd be great to hear your extended thoughts on this, so we can include it as a record of the meeting.
Daniela, I think you're still on mute.
Sorry, Neil, I think that I will invite you to add your question in the document, and maybe we can come back later. The next speaker today is John Sinoka from ECCC, and he will talk about GEM and CAN-RCM. So, John, the floor is yours. Okay, we can see it.
Okay.
Yes.
Okay, good. Well, thanks very much. So I was asked to talk about our efforts on CAN-RCM, and this work, as you can see, involves a large number of people, whether it's on the physical side or on the technical side, to sort of bring us to where we are now. And sort of looking back as to how we got a regional climate model, our primary goal in initiating this effort some time ago was to downscale, the predictions and the projections made with our global model over a regional local domain, and the sort of domains we've done so far from this Cordex intercomparison project in North American, the Arctic, the African domain, probably also the European domain. And I should say that it's a dynamical downscaling. You run the global model first, save the output, and then that output is used to drive the regional climate model in a one-way direction after the fact. So when we were trying to put this together, we didn't have a lot of resources, and the idea was, well, let's use the exact same physics package we use for our global model in the atmospheric model of our ESM, in the regional climate model. So it's run only in atmospheric mode, the regional model currently. And so we have our spectral model here with a dynamical core and a physics package, and then we sort of look around for what's a good regional model that we might be able to use our physics in, and the one that we settled on is the NWP model, the GEM model, the semi-Lagrangian model, and we started with GEM 3. So it has its dynamical core, which is semi-Lagrangian. We're not interested in using their physics, so we went through this laborious exercise of transferring our physics package into the GEM model. This is some years ago. And the idea is that we would use the identical physics package that we used, and at that time it was for CMIP5. And that sort of constituted our regional climate model, as this GEM model can run equally well globally and in limited area mode. The kind of wrinkle, the benefit we would suggest that our approach has with this sort of strict physics compatibility between the global model and the regional model, it sort of offers advantages. And there's 4 of them listed here. And these advantages would be advantages over, say, just a group that does regional climate modeling, the association of a global model with a regional model using the same physics package. You can talk about the development, the physics development and its scalability, because you can run it over a series of resolutions while you're developing it equally well in the regional climate model in principle. There's this issue to do with domain transferability. When people develop a regional climate model, they typically develop it over their home domain, and they might be developing things and making decisions based on the geography of that domain, which could get them into a bit of a trap when they move it somewhere else in another domain that doesn't perform as well. Well, our physics is basically run globally and regionally, so we kind of make compromises and understand those behaviors around the globe, and so we don't fall into that trap as easily. Another thing is the driving fields of the regional model. Typically, regional climate models can only be driven on their boundaries by the primary prognostic variables of wind, temperature, specific humidity. There's a lot more of other prognostic variables in these Earth system models now, like chemistry, tracers, and aerosols, and so forth. But each of them have their own formulation, their own approach to doing advection, and so they're not going to match in principle between any global model and a regional model. So regional centers typically have to put 0 on their boundary conditions, and they have solutions for only sources and sinks within their regional domain, whereas we have every single prognostic variable to drive the regional model on its boundaries because we share the same physics package. And we even have an approach to do that for other models or observations by slaving our model with a nudging approach to put the meteorology in. So there's a benefit there. And then finally, the concept of value added. You hear about this all the time for regional climate models. Because we run a global model, and we have to run that experiment first. Any experiment, climate projection, climate change experiment you do in a regional model, you have to run a global model first. In principle, we have an answer to any question you might want to ask. So the question then becomes, when you run the regional model, how have I improved upon that answer? How is it different? Is it better? And so we have more pointed questions about that because we've already done the global runs, and this is a big expense to run a regional climate model. And kind of on that point, I just want to show this. This is a kind of an analysis of the change in precipitation from the end of the 21st century to the end of the 20th century for the global model, CANI-SM2 for CMIP5, over 5 ensemble members for future scenario RCP4.5. And this is the percentage change in precipitation you'd see from the global model on average from those 5 ensemble members. This is what you would see when you downscale each one of those ensemble members with the regional model. And of course, you see all this extra structure present, which is what attracts people to the regional models. If you do a straight difference between them, what you find is a lot of structure in there, and you say this is potentially where the regional model is doing better. But really, is it? There's a lot of variability between ensemble members. So really what you want to do is look at a standardized difference between these 2 quantities with the standard deviation of the between ensemble members and, say, the global ensemble. When you do that, a lot of this picture clears up, but some things stand out, like 4 to 5 standard deviations of difference between the regional model and the global model. We'd say that this is an appreciable difference for this ensemble size. You can even use statistical significance and clean up some of this picture even more, but this really sticks out. And if you take a look where that's coming from, the GCM topography in this region and the RCM topography are significantly different. And you get benefit from regional climate models primarily at leading order from the surface processes, not so much from, say, stronger fronts in the interior of the atmosphere. And something you get for nothing, which we did for CAN-RCM4 in our initial implementation, is higher resolution topography. So it's being forced. So you can see there's a big difference here. Then you want to go a little bit closer to say, is that a physical improvement, which would require validation, and you have some physical arguments because there's a physical effect of the surface topography making it improve. So we like to apply something like this appreciable difference analysis when we look at the regional climate model to sort of understand where we're getting benefit. For this CAN-RCM4, we applied it for this Cordex project. Their historical, not historical, but observational driven runs over the historical period, historical driven runs with our CANI-SM2, and some future scenarios at various resolutions with ensemble members. When we produced the CANSICE large ensemble with CAN-ESM2, 50-member ensemble global, we downscaled each one of those 50 ensemble members with CAN-RCM4 at 0.44 degrees and did some sensitivity tests of 0.22, and this future scenario of strong climate change, RCP 8.5. And then we also did some investigation of running the regional climate model for a couple of different seasons with our seasonal forecast system at both 0.44 and 0.22 degrees to look at improved skill regionally with the regional climate model. So, I mean, CAN-RCM4 has been used for a large number of national, international peer-reviewed scientific studies and assessments. A large number of universities have used it. Regional climate consortia like PKIC and Uranus have used it. Federal departments and provincial ministries. So it's been quite well used, and we're expecting the same for CAN-RCM5. And now for CAN-RCM5, as Neil described, we're going to be bringing our physics into GEM right through the same repository. So this is a huge improvement. That was a really laborious task, moving the physics across and ensuring it's the same. There were two different code bases. Now they come from the exact same repository, so you're guaranteed that. And the GEM model has been improved to provide an interface to switch between physics packages, and they call their own physics package through this interface, and we can switch to the climate physics package. And so because this is going to be our regional climate model, as it has always been, and we have this nice connection, we're testing, as Neil said, this GEM 5 with our CAN-AM5 physics in global mode as a new dynamical core for the ESM, the atmosphere component of the ESM. So that's an improvement. Okay, so what else is improved in CAN-RCM5? We have still this global, coordinated global and regional modeling approach, so we still maintain that. There's a full updated physics package going from CAN-AM4 that we use for CMIP5 to CAN-AM5 CMIP6, and Jason will be discussing that, I guess, after the break. And some extra new kind of wrinkles that we use is the application of runtime bias corrections, which we've been working on at CCCMA, where rather than just driving the regional climate model with the output of CAN-ESM5, we have an approach that Slava Haran and I developed that you can bias correct the atmospheric component running in AMIP mode of the ESM and bias correct the surface forcings to improve the circulation that's driving the regional climate model. And then you can do that, you can take a look at, and that was demonstrated in this paper for seasonal prediction, improving it. You can also, there was a recent paper with Gerhard Krinner that we developed when he visited CCCMA, where three climate modeling centers did idealized experiments where we applied this procedure to demonstrate that the improvement you see in the historical period is by and part largely preserved through the 21st century, even under very strong climate change, the improvements in the circulation through these idealized experiments. And so we're looking forward to having improved driving of the regional climate model as well. These runtime bias corrections can also be developed within the RCM, and that's currently under development as well. And then also we'll hear about from Jason is we have lakes in CAN-AM5 compared to CAN-AM4, thermodynamic lakes, the Canadian small lake model that Murray McKay developed. This is a thermodynamic lake model, which is okay for subgrid scale, but when you get to the regional scales, you have many, many points, say, making up the Great Lakes. These thermodynamic lakes do not respond well. They're not connected to each other. And so to mediate that, we're thinking of doing runtime bias corrections of the surface water temperature and lake ice to improve the behavior and make them collectively act together, kind of like the old days when you had slab oceans for global models and use flux adjustments to be a proxy for transport. So those are some wrinkles there. And then finally, this is my last slide. Applications. So of course, we're going to be doing Cordex for CMIP6. We're looking forward to having the regional climate model have a deeper integration within CANSIPS, our seasonal prediction system, and CAN-ESM5 for climate projection. So to run on a more regular basis, to be an easier tool to just switch on when you want to have a downscaling of an experiment. Also, it's going to feature prominently in this flood hazard identification and mapping initiative, which is a large 3-year proposal led by NRCan, but there's a climate change component which we're participating in, and the output of CAN-RCM5 will support research done at Uranus, PKIC, and several universities across Canada. We've already discussed with people at Oregon State University about using the output of CAN-RCM4 and then upgrading the CAN-RCM5 for impacts on security and of the electricity transmission and distribution system for Portland General Electric. These improvements in the lakes were hoping to improve estimates of lake water levels through producing net basin supply from the regional climate model, which is a critical component, and hopefully improving that and maybe helping with things like flooding in the Ottawa River Valley. And that's what Frank Soklenix at Water Resources and MSC, and also other projects such as using the driving data from CAN-RCM5 to be used by other regional climate models to downscale even further for climate impacts over the Sailor Sea. So these are just some initial things that CAN-RCM5 will be used for, but I imagine there'll be many, many more like the last time. And I guess I'll just leave it there and ask for questions.
Thank you, John. I cannot see any questions in our document. Maybe, okay, I can see. Do you have a question?
Am I the only one with my hand up? Because you've heard from me a lot. Okay, all right. Yeah, thanks, John. It's really exciting stuff. So when you get to the point where you're, you're starting to move away from, if I understood this right, which I could easily have gotten wrong, with CAN-RCM5, you're actually starting to get into bias correction and really, correcting the boundary conditions that are driving the regional model. So that, and the trade-off there, I guess, and correct me if I'm wrong, is that there's less of that kind of complete consistency between the driven model and the outer model. Is that, so do you see that as kind of a temporary measure, or, I mean, there's always going to be biases, right? But if it becomes like more and more of the practice, is that sort of blurring the lines a little bit about this, this really pure kind of view on value added? I think it sounds really interesting, by the way. But I'm just curious about what how you're thinking about this philosophically.
Yeah, I mean, as you say, there's always going to be biases in any model you produce. And what we like to say is that, what do you use a climate model for? You use it to make predictions and projections. And if a bias correction can improve a prediction, then you would want to use it. If it improves the projection, you would want to use it. I don't know if it kind of breaks the compatibility between the two. It certainly improves the behavior of the models, but because they're using the same physics, you're correcting generally large scales, the bias correction is a climatological correction to the basic state. And that's shared between the RCM and the GCM. In fact, doing bias corrections in the regional model itself, one of our initial things was we should just use the bias correction that we derive for the global model within the regional model, right? That would be a first estimate. You're still going to get a little bit of benefit from probably doing it within the RCM itself. But I think to the extent that it improves a model and allows you more latitude, it's a very useful tool. The concern would be if it sort of degrades your model in some sense, your predictions or projections. And there is the potential for certain things that you may want to look at that it might, but it ends up just being a cyclostationary term on the right-hand side of the equation, just an annual cycle of a forcing or a warming or a cooling. So it really doesn't interfere with the model. So it's demonstrably helpful, it seems.
Let's, Danielle, I suggest we take Philippe's question because, as I said, you've heard a lot from me. So.
Yeah, okay.
Hello, John.
Hi.
Nice talk. I'm interested to know more about your bias correction, as Paul mentioned. So are you correcting toward a reanalysis, or are you also correcting the 3D fields, or just focusing on some 2D fields? I guess you correct the mean and not the variability. So please explain it a bit more. What is it?
Sure. I mean, so at every grid box in the atmospheric model, the winds and the temperatures and the specific humidity are nudged in something like an adaptation run of the AGCM component of the ESM. So you have observations, reanalysis data set, and you would nudge in the meteorology, the winds, the temperatures, the specific humidity on the large scales. And all the while outputting those nudging tendencies to the output of a model. And when that run is completed, say a 30-year run, you average up those nudging tendencies to produce a climatological annual cycle of the average, let's say, force, if it was the winds, or the average warming or cooling that you put in that grid cell. And so what you end up with is just in each grid box, an annual cycle, say daily or even 6 hourly, when you average over all the ensemble members, and you smooth it a little bit too, of a force or a tendency on the winds or the temperatures, or the specific humidity. And that cyclostationary forcing just sits on the right-hand side of the model. And so that can be run at any time. You can run it back in pre-industrial, you can run it in the present day period to evaluate how much you've improved the present climatology of the model. And then you can use it going out into the future as well, because it's just a stationary term on the right-hand side of the equations, these bias corrections.
Thank you.
Thank you, John. Thank you, Philip, for your question. So now our next presentation, for the interest of time, is about Classic. And Vivek from ECCC and Joe Melton from ECCC as well will present about this. Vivek, let me know if you have issues.
Yep,
sharing
thanks,
something.
thanks, Daniela. I will share my screen. Okay, can you see my screen?
Yes, we can see it.
Okay. Okay. All right. So, like any other climate model, you have to have a land component. And the land component we have in CANISM, it's called Classic. And that's what I'm going to talk about. And Classic stands for Canadian Land Surface Scheme, including biogeochemical cycles. A lot of you may already know this, that Classic has evolved from CLASS, which was developed by Diana Verseggi, which does the physics, and biogeochemistry, which is CTEM, which I worked on early in my career. And so Classic has evolved from CLASS and CTEM. And we are now a team of about 5 scientists at the Climate Research Division that work on Classic development and evaluation. So although we are a small group, I would like to say we are a more coherent team than ever before. So I will try to summarize primary science capabilities of Classic and tell you that in CANISM 5, what we have is Class CTEM, and we are currently replacing Class CTEM with Classic. So, like I said, the CLASS land surface scheme goes back to 1990s, was developed by Diana Verseggi. A Canadian terrestrial ecosystem model, which does the biogeochemistry, I started working on it in early 2000s, and then Joe Melton joined our group. And both models have always been coupled, but more recently, Joe has implemented more technical features, including software containerization, self-documentation of the code, and Christian in our group, Christian Seiler, has put together some software that benchmarks the model output against observations. And on these changes, launched Classic as a community model. Now, it is a very complex model. It has almost every land surface process you can possibly think of. Of course, it's not perfect. Model keeps on evolving, but this graphic shows we do energy fluxes, water fluxes, and CO2 fluxes. That's a biogeochemistry component. And we also have methane emissions from wetlands and fires and soil uptake of methane. So, and because we do biogeochemistry, vegetation is a dynamic component of the climate system. So the leaves come and go depending on the climate. The vegetation grows and dies depending on the climate. Okay, let me move to the next slide. Okay, so we are currently in process of replacing CLASS and CTEM with Classic. And it's essentially the same model, but it has been improved over the years. It has a few more processes, and we are working such that Classic will become a sub-repository of CANISM. And when that happens, the idea is that we can use the same code base, the same Classic code base for offline Classic simulations, which Joe will talk about, and we have done for a very long time. And then in offline simulations, we drive the model. We can drive the model at a single point, like a FluxNet site, and we drive it with observed meteorological information. Or we can drive the model at regional and global scales, driven with reanalysis data. But of course, when Classic is coupled to the atmospheric component in CANISM, it sees the climate that the climate model provides. And up until now, we have run Classic both offline and in our spectral dynamics-based CANISM at the T63 resolution that a lot of you are familiar with. That's about 2.81 degrees. But as we move towards the GEM-based CANISM, we will have a nominal resolution of around 1 degree or finer. Offline, we have also started to run Classic at 1 degree resolution. So these plots show gross primary productivity, which is a measure of photosynthesis, and the two model resolutions, the global model resolution that we run Classic offline at. So it's nice to see higher resolution. It looks beautiful. But of course, it means putting together data sets at both resolutions. We still want to keep running at this coarser resolution because it allows us to do model development fairly quickly. So there are about 2,000 land grid cells for the coarse resolution and about 17,000 grid cells for land grid cells, excluding Greenland and Antarctica, that we do not run offline at this 1 degree resolution. Okay, so in terms of science and technical capabilities of Classic, which we currently have in CANISM 5, of course, on the physics side, land surface component has to do energy and water balance. There's a single snow layer, there's a single canopy layer, and of course, snow and rain being intercepted at the canopy, the sublimation of snow, evaporation of intercepted water from the canopy, and then the snow melt and runoff. The model has the capability to use any number of soil layers, but up until CANISM 5 and for CMIP 6, we used 3 soil layers. And that has been raised as an issue because we do not do permafrost properly. And of course, you may know, to do permafrost properly, you have to go down deeper, you have to do more soil layers, so you have that thermal inertia when warming happens. And so offline, we do 20 soil layers, and we go down to 60 meter. On the biogeochemistry side, again, you have to do this basic carbon balance. You have to do photosynthesis. You have to do respiration. And like I mentioned, the vegetation is dynamic in CANISM 5, and it grows depending on what the climate is. Leaves come and go at different times of the year, depending on what the climate is. Fire and competition, they have been in the model, but we have never evaluated them. So all these processes in red, once Classic gets implemented in CANISM, we want to evaluate these processes within the CANISM framework. So there's fire, competition between plant functional types, that's the horizontal vegetation movement. So as the climate warms, you will have vegetation moving northwards in the northern hemisphere, for example. We have also recently implemented nitrogen cycle, and that constrains carbon cycle. So the model doesn't photosynthesize like crazy when CO2 increases, which was the case for CMIP 6. CANISM 5 was one of the models with the highest land carbon uptake. So inclusion of nitrogen cycle will help fix that. And then now that we have more soil layers, we are also including permafrost carbon-related processes. So as the soil layers thaw, there will be carbon released from permafrost carbon, creating the permafrost carbon feedback. Okay, so in terms of timelines, like I said, we are replacing Class CTEM with Classic. This is a boatload of technical work. We have been at it for more than a year now, and being a small group, there is so much speed we can work with, and we do not have a lot of technical help. So a lot of scientists also end up doing a ton of technical work. So the hope is that we will have Classic implemented in the spectral dynamics-based CANISM version at the end of this year, but we are keeping our fingers crossed. So I will let Joe take over for the next 3 slides.
Yeah, thanks, Vivek. So what I was going to just give a little overview is a bit more what we're doing in the offline world, but also what we've done around the community aspect of Classic. So on the right there, you can see how land surface modeling has been evolving through time. And it's just been generally increasing with more and more processes being added into these models. And as the number of processes increases, we're also looking at them slightly differently. We're trying to think about how we can, on this subgrid scale, try and account for these processes that we know to be important, but are happening, not just across the grid cell as a whole. Now, Classic, the nice thing is, we have this kind of rather long development history. I mean, we presently contribute to a lot of different projects, like the Global Carbon Project, recently ones like ECMIP, and when we do these contributions, we actually find that our model is quite good. We're looking quite good compared to other models. And I think a lot of this comes from the fact that we had a very strong history that started with Diana Versteges with Classic and then Vivek with CTEM. So we built upon a really solid foundation. But this increasing complexity is making it harder and harder for us with such a small team to manage the model as these number of processes we need to include becomes higher. Can you go to the next slide, please, Vivek? So our approach to this has been to move towards a community model to try and harness so the energy and expertise of the Canadian research community to help us maintain a state-of-the-art model, and also to just get more use out of the model. And so right now you can see these are at the moment offline development analysis activities that are being done both internally but also external within the Classic community. And it's these sorts of model developments that will feed into CANISM. And some of these may not make it into CANISM 6, but potentially then down the road for the next version of CANISM. And so thus far our kind of experience with a community version of our model is evolving and changing through time as we work with the community and try and figure out how to best bring in the science that is being done, and also to maybe motivate other needed science. But thus far, it's been a very interesting process. And I think like CANISM, the collaborative version, will also have a lot of figuring out to do through time. Can you go to the last slide, please? So right now, our model is being run rather routinely at the site level, regional and global scales. And that's been very helpful. We're getting a lot of better understanding, deeper understanding of our model. But this future capability to have Classic go from the offline to the coupled world, I think is one thing that could be potentially of interest to this audience, because you're able to then develop the model at the site level, so you can really get a nice, good understanding of how the processes are working that you're interested in the model. You transition to an offline global run, so therefore you have that nice control of a prescribed climate, and you can understand the global impact, and then you can transition that into CANISM, and you can see what's the climate impact. So I think that could be a really powerful kind of development chain or analysis chain, and hopefully that'll interest people in this community. Okay, thanks. I'm done, Vivek.
Okay, thanks, Joe. Oops. Okay, so offline, like Joe said, we evaluate the model offline rigorously. We do site level simulations, regional simulations, global simulations, and that occupies a lot of our time. And as the model has become more complex, that's taking more and more of our time. What we haven't done is evaluate the performance of the land component, be it Class CTEM in the older model version, or be it Classic going in future. We haven't evaluated the land component's performance in the coupled mode within CANISM. And some of the examples I'm listing here just to give you a flavor. These are the things I've been thinking of doing, but never had the time to do that. So the strength of the land atmosphere coupling, for example. Now vegetation has a memory, just like soil moisture. So, and it affects precipitation variability. And talking with Bill Merrifield in our group, who does seasonal forecasting and decadal forecasting, he said that vegetation memory, it does improve precipitation variability, but I have never been able to quantify that. Then there's the effect of climate change on the physical and biogeochemical land surface processes. So these are your usual climate change scenarios going in the future. And if you remember, there was talk about growing 2 billion trees in Canada. So you can do a simulation. If you plant those trees in Canada, what effect will it have on the Canadian climate and global climate? Because you have all these feedbacks, you're sucking up CO2, but you're also increasing the decreasing the albedo, because planting trees means darkening the land surface. So there are a lot of these coupled land atmosphere interactions that can be investigated. So in summary, we have had a good relationship, and Joe has led that effort with the offline land surface community. So this is your typical FluxNet community, and people who want to run model at a side or globally and see what the model does when driven by reanalysis data. But we haven't been able to develop connection with the coupled land atmosphere community. So we are hoping that this forum will lead to that kind of interaction, and hopefully we'll have more connections. And as CANISM turns into a more community usable tool, we welcome and encourage people to evaluate these climate vegetation interactions and atmosphere land coupling, and these and processes that can only be evaluated within the coupled mode. And we are hoping that we will have a version of CANISM working by the end of this year, and for distribution sometime next year. But it would still be the spectral dynamics-based version. Thank you. Okay, let me stop sharing my screen.
Thank you, Vivek and Joe. Great presentation. Let's see, I can see, yeah, Dr. Kirsten, you can unmute yourself.
Thanks, Vivek and Joe. So these are really exciting developments that I think will allow us to answer a suite of very interesting and actually timely science questions. So first, the first one is a comment. Vivek, you mentioned that there's little collaboration so far with the coupled community. So I'm happy to actually let you know that the proposal that we submitted under the CAF call was successful. So hopefully we'll be able to use that to do some work, especially on the afforestation component of the model. And then I have a question which I think may be directed to you and Joe, as well as to Neil, which perhaps Vivek builds a little bit about on the question you had earlier. So to me, it is not entirely clear in this community-based CANISM approach how new developments will actually be ported, so that the the community external to CCCMA actually be able to use that. So if one of you could elaborate a little bit more on that, that would be great. Thanks.
Yeah, I will let Neil address that.
Okay, so I think we'll speak a lot more probably about this tomorrow too, but basically we have a process for integrating changes into the model that has a whole testing regime and scientific evaluation and all of that. So once like Vivek and Joe and their team implements new changes, and those are integrated into kind of our main CANISM branches, basically by default, it's exactly like the code that we use for this collaborative CANISM and the code that we use internally is literally the same code. So yeah, it should just kind of seamlessly become available as it kind of gets merged in. So there is sometimes like a little bit of a delay. You know, we have to make sure that everything's working on the different platforms and that kind of stuff, but basically it's the same code. So like, you know, the code that's being used now is exactly the same code that we ran for CMAP 6, for example.
Yeah, Thanks, Neil. And I just want to add to that is that on the land side, we have the ability to run the model offline. So if new parameterizations are proposed, we will evaluate them first in the offline model at a single site and regionally and globally and see if we don't break anything and the parameterization is doing what we expect it to do. And once it has been evaluated offline, then of course, since the code base is the same, it works its way through into the coupled model. And again, we will evaluate into the coupled model as well. And this is the philosophy that John Sinoka promotes, is that every time we change any parameterization, you run a control run, and then you run your change parameterization run and see what differences there are. Have you broken anything? Have you changed anything? And we have run into surprises in the past. So sometimes things seem intuitive, but they may not be. And it's a couple feedbacks that that can throw surprises at you.
Thank you.
Thank you, Dr. Kirsten. Maybe, well, I cannot see any questions in our share file. I don't know if someone else has a question.
If I may add just one more thing.
Yes, sure.
Is that we do model development. There's a ton of model development. And there are people out there who say you have to include this process, you have to include this process, you have to include this process. So yes, you can keep making a model more complex, but it's the application of the model and producing climate impact results that, in my opinion, are more useful for the community out there, for the people, for Canadians. Yes, we can come up with a fancy parameterization and improve our process, but at the end of the day, it's a climate impact. So model application, and we, in our name, we are CCCMA, climate modeling and analysis. So we do modeling, but I think we are light on the analysis part. So, and the CANISM large ensemble example that John Fife analyzed, that was a good example of taking that ensemble and producing good science out of it. So I am of the opinion that it's the application of the model, which we are not able to do as a small group. We are always busy with model development, and once you have a model this complicated, there's always maintenance going on. So something breaks and something else breaks, and you're always maintaining the model. You have new geophysical fields coming in, you change the land cover, you change the soil data set, and then you have to evaluate the model again. So if the community out there can help with model evaluation, its application, I think that would be a benefit. But that's my 2 cents. I don't know what others have to say.
I agree, Vivek. I think that there's I think the vision here is quite well aligned with what you're describing, right? But there are also applications where there's still scope for having an outside community work on enhancing the capacity of CANISM for various research purposes. So we've been talking about, if, for example, in our proposal, we talked about bringing back the slab ocean model capability of CANISM, which isn't a priority. I mean, it's not the highest priority thing internally at CCCMA, but there is a lot of good research to be done with that, I think. So I agree that there's a need for sort of more downstream work than upstream work, but at the same time, as Neil described, the 40, it's just a long gap in sort of technical development. It's possible that the university community could assist with some of that. I take your point, though, that these models remain completely underanalyzed, including the one you have right now, right? I mean, there's so many opportunities to work with the model and do slight perturbation experiments to try, just to try to test out a few ideas. So I think there's scope for a lot, but yeah, the real question of prioritizing, figuring out which are the highest priorities, that's the hard part, and that will depend on resources and interest and all that. Yeah, but I take your main point very well. I think Phil we hadn't heard from Phil yet, so and then John.
Yeah, so I mean, I agree on the analysis emphasis as well. I'm wondering whether there's a possibility to negotiate with AWS and Google and Azure to get intermediate or research products onto the commercial cloud in the same way that NCAR got the large ensemble, right? I mean, that's supported. NCAR doesn't have to pay for that. And it's wildly accessible, so anybody can actually use it. But it costs, I mean, there's no funding for that ourselves. Storage is expensive. But do we have relationships with the Planetary Computer team or Google Climate or any of those people? Because it does seem like opening up some personal contacts would be fruitful if we had something to put there.
Yeah, I agree with that. I think a couple of comments. I mean, like I've attended some of the seminars that they've held where they've said, okay, you can make applications for these kind of resources. I know that more broadly, Environment Canada has approached them. I haven't heard what the results of that have been. That was at a higher level than us. So yeah, but I think it's a good idea. I just wanted to mention though that we are doing that to some degree within this remit of the cloud computing aspect of the Compute Canada proposal. So it's not commercial cloud, but it's the Compute Canada cloud. In fact, that was a kind of community resource that we did get sponsored. So yeah, we hope to make at least some of this same kind of capacity, like Jupyter Notebook enabled analysis of data sitting on a cloud server. It'll just be through, in this case, the Alliance cloud rather than commercial cloud. But yeah, we could do both.
And I'd just add that for one person, Orion Abernathy has a ton of contacts with both US government agencies and with all the commercial providers. And so Pangeo and just leaning on Ryan's sort of experience with this is also a useful thing to explore, I think.
Yeah, so far our rapporteurs can make a note of that idea because I think it's come up before, and we should explore that further. Sorry, I interrupted.
Thank you, Philip. Maybe John, you want to unmute yourself and comment or ask your question? John Sinoka, you have your hand raised.
Sorry, you're talking to me? Sorry.
Yes,
Okay.
you have your hand.
Sorry, I missed that. Yeah, just to follow up on what Vivek was saying about, I mean, he's outlined the difficulties associated with development. And when I see the plans, I see the word development and application and analysis with CAN-ESM. And there's one extra thing that Vivek hasn't pointed out. When you do development, it's somebody could develop a wonderful parameterization and be a real expert in collaboration with us. However, if that person moves away and goes somewhere else, you're left with a piece of code without that expertise. And one thing we've learned over a very long period of time, you need resident expertise on every single parameterization. Somebody's got to take responsibility for when you look at the model and try and understand what it's doing and why it's doing that. You go to sometimes those experts. Those parameterizations are sort of living entities that need to be evaluated on a constant basis and updated regularly. And that's a difficulty that we've always found. So that our best collaborative work with universities has been really tight, close connectivity with a scientist within CCCMA who has that similar expertise. And that scientist within CCCMA would then, I guess, take responsibility for that parameterization afterwards, getting all that leverage and expertise from the outside. So it's something, I'm sure we'll talk about it maybe tomorrow as well, but it's sort of a development is a bit of a difficult issue to have that kind of longevity and support ongoing, which is absolutely required. So how we go about doing that is I think a really important question.
Thank you, John. Okay, following our agenda, we have a break right now. Maybe we can reconvene again at 2:30 p.m. So we will stay here and take your time until 2:30. Paul, something that you want to add before going to break?
No, thanks everyone for the talk so far. And yeah, looking forward to seeing you starting at 2:30 sharp.
Let's see, 1 minute more.
Hi, Michael.
Hi, Paul. Is my audio working?
Yes, Michael,
Yeah.
we can hear you. I think we are ready to go. Thank you, everyone, again. Thank you for the last speakers. And we are now to present our first presentation for the second block of sessions. It's about the analysis for development, A4D, and CCCMA published data presented. So I welcome Michael Sigmund and James Anstey from ECCC. Let me know, Michael, if you can pull it up. Yeah, we can see your screen.
Great, thank you very much. Let me get.
The only thing
No,
is,
I cannot see my presentation.
yeah, we are
Sorry?
seeing your notes. I mean, we're not seeing the presentation mode.
You see it now?
No, we are still seeing your
Nope.
notes. No.
I have done this before, but not as often as others because we're not using Zoom. Let me stop sharing. I'll just share my whole screen. Maybe that's easier. Can you see it now?
Yes, we can see it.
Great. All right, thanks, Daniela, and everyone who's organizing this workshop. So I'm Michael Sigmund, and myself and James will be presenting about analysis for development and published data that can be used to evaluate the model. So as you can see, it's a whole team effort that yeah, there's a lot of people have contributed to the results that I'll show here. So what is A4D? Well, basically 2 years ago, we at CCMA realized that we need to have more and more coordinated model analysis to support the development of KNISM. So in early 2020, we established the A4D activity. So CID is a Climate Research Division, so it does not only include the CCMA, but also other sections. This was just before the pandemic. I think we had one in-person meeting, and then the rest was all online. So the goal of A4D is to establish a comprehensive process to through which KNISM output is analyzed in a systematic and ongoing manner, with the ultimate goal of improving the model, future model versions. So what is that A4D process that we've established? Well, it's not very complicated, but first we start by collecting and documenting the systematic model biases in an online archive, and for that we use a GitLab issue tracker. This is a screenshot of the tracker as of last evening. And so we currently have 17 issues, 14 of which are model biases. And then for each issue, we have a short description, and then which follows with discussion and any updates. So after documenting these model biases, we've established working groups with working group leaders that are leading all these efforts. And then those working groups do the actual analysis, and then we discuss these issues during monthly A4D meetings. And then the idea is to report the results in either standalone deep dive papers, and for that the special Kinesim 5 GMD issue is an ideal platform for that. I believe we have 4 papers there now. But we're also working on a group Kinesim 5 analysis paper for later this year. So in the coming few slides, I'll highlight a few of the issues that we've discussed during these meetings. And the first one is spurious stratospheric warmings, which Neil also mentioned before. So the issue was that Kinesim 5 features these large spurious non-physical stratospheric warmings in summer. So here on the right, we are looking at monthly data of 5 historical simulations with Kinesim 5.0. It's the global mean lower stratospheric temperature. You see these spikes in green related to volcanoes. Those are not physical, but the non-physical warmings that we're talking about are highlighted by these dots here. And it appears that this was caused by spikes in mineral dust, in coarse mineral dust, and these spikes were caused by physical mass fixer corrections. So these mass corrections are implemented in the model to ensure that the mass of the advective hybrid tracers is conserved, and the default hybridization parameters cause these mass corrections to be of large positive values for dust tracers, which then triggered some kind of positive feedback, resulting in artificial dust bursts propagating to the lower stratosphere. So that's shown here. And by retuning these hybridization parameters, Slava, Karin, and others were able to get rid of these spurious dust spikes, and with that also the spurious stratospheric warmings. And as Neil mentioned, this is one of the only physical changes that went into Kinesim 5.1. A second issue that I wanted to highlight is from the ENSO working group led by Bill Merrifield. So it appears that the ENSO in Kinesim 5 is too weak and has an incorrect seasonality. So shown here are the seasonal cycle of the monthly near 3.4 standard deviation in observations, Kinesim 2, which is basically the same as Kinesim 4, and then Kinesim 5. So here you can see that Kinesim 4 had a really almost perfect El Nino with a good seasonal cycle peaking in December, and also a good magnitude. And this really helped with our seasonal predictions. But in Kinesim 5, which we also would like to use for seasonal predictions, this seasonal cycle is a bit off. The ENSO peaks in March and not in December, and it's generally a little bit too weak. So a possible causal factor for that, identified by other groups in papers published on CMIP6 models, they suggest that the biases in this ENSO seasonality arise from the biases in the equatorial Pacific SST seasonal cycle. And there's 2 solutions that this working group has considered quite successfully so far. The first one is this systematic tuning exercise that John Sunoka also already mentioned. So systematically varying 9 Caniem5 parameters, and then tuning for a few metrics, including the NIA 3.4 standard deviation. They're able to get a much better seasonal cycle and also better amplitude, as shown here. And then the other approach that they are using is this, which was also mentioned by John, is the runtime bias correction. John already explained how this works, but just to say that this has been successful in the sense that it has reduced ocean biases. The answer strength and seasonality is also improved. And there's fine-tuning this approach and combining it with the first approach to get an even better answer. Climate sensitivity. This was a big one for us because CANISM5 has the highest climate sensitive of all CMIP6 models, as you all know. So Jack Virgin and Jason Cole and others have done a really nice analysis, which has been published in this GMD special issue for CANISM5. And they found that the ECS increase in CANISM5 relative to CANISM2 is due to a more positive shortwave cloud feedback. And they also found that the spatial pattern of the surface temperature change impacts the magnitude and the distribution of the low cloud response, which again are important for these shortwave cloud feedbacks. And then this objective CANISM5 tuning, as already mentioned, led to a lower ECS, 4.6 Kelvin now. So Jack did a quick analysis on some early simulations and found that it's really the shortwave boundary layer cloud feedbacks that are weaker in this P2 version than in the P1 version and also in CANISM 5.0. All right, so some results from other working groups. Atmospheric circulation, we looked at the stratospheric warming frequency. So these are the physical warmings occurring mostly during the winter. I found that there's generally too few certain warmings in CANISM 5, whereas there were too many in CANISM 2. And so this also could have implications for seasonal forecasts because stratospheric warmings have are a source of seasonal predictability. And yeah, so we found that these changes between CANISM 5 and CANISM 2 are related to changes in the orographic gravity settings. And we did some retuning to get rid of this bias. Then we have a cold bias of the Himalayas related to high albedo. This is work that's led by Jason Cole, Vivek, Aurora, and others. Then we have too much sea ice in the North Atlantic, and we have a winter cold bias over sea ice. And we have a mismatch between top of the atmosphere balance and AMIP runs versus coupled runs. And all these things are under investigation. I briefly wanted to mention another activity within the A4D group that is going on, and that's the development of a standardized diagnostic package. And this is to address the need to track model biases from one model version to the next in a systematic manner. So this is work led by Kathy Reeder. We were able to hire as a contractor for a few months. So this work is based on a community tool, EasyML tool. So we previously had in-house tools, but they were not community tools, and it was pretty hard to maintain them. So we switched to a community tool, and we are trying to build it such that you don't really need to know a lot about ESMBL tool or Python to use the package or even enter new diagnostics. So for this part, I'll conclude that, well, so A4D is an activity that encourages and coordinates analysis in support of model development. We were able to make some progress, but we are constrained by limited human resources. A lot of the people who are involved are also model developers. So we really need help. So we are calling for collaborations. So please contact us if you'd like to contribute to a working group, if you have identified a systematic error and want to start a new working group, or just want to participate in A4D meetings to get to know more about this effort. Yep, so these are our email addresses. And with that, I'll hand it over to James. I'll actually advance his slides here.
Okay, thanks, Michael. Yeah, so just to say a very quick word here to build on what Michael just said, to give an overview of the data from CANI-SM5 that is available from the ESGF. So a considerable amount of output for CMIP6 has been published for CANI-SM5. This plot on the left just shows the data volume. Publishing is a function of time. Bulk of publishing, of course, is done at this point. The plot down on the bottom left shows the accumulated volume published over time. So it's got up to about 300 terabytes of CANI-SM5 output that we host on our CRD ESGF server. And approximately a petabyte has been downloaded worldwide from this server, and about 300 terabytes from replicas. In other words, the same data just replicated. Some of the same data is replicated on other ESGF nodes. Michael, could you go to the next slide? So just to give a sense of what that volume means, according to the ESGF dashboard, this is a site maintained at CMCC in Italy that tracks worldwide downloads of ESGF data. The worldwide volume to date, according to this site, is about 30 petabytes. So the total for CANI-SM5, about coming up to, I don't know, 1.5 petabytes or something, is fairly significant. Considering it's one of about 60 models that have published the historical CMIP6 simulations. Next slide. So this kind of gives an overview of the simulation years. Quite a lot of simulation years have been done for CMIP6, as shown in the plot on the left, where the experiments are categorized by the MIP. So the CMIP category, for example, would include the historical and DEC. And then the published data volume by MIP and Seymour table is indicated on the right. So probably everyone here knows what a Seymour table is, but just to say, this is basically a collection of variables grouped by temporal frequency. So for example, AMON is monthly atmospheric data. Next slide, please. And this is just to highlight one thing that's been mentioned in talks already, that large ensembles are available for CANI-SM5 with a lot of data available on ESGF in a lot of variables. So these are similar to the plots on the previous page, but now experiment is shown on the y-axis. It's still Seymour table on the x-axis, and colors tending toward green or blue are a large number of ensemble members. So for example, for historical, 65, this is counting P1 and P2 versions of the model, which in general, most of the ensembles here coming up to 50 are a mix of those two versions of the model. So in particular, I'll highlight on the left here, a lot of ensemble members available for historical and most of the SSPs, the future scenarios. Next slide, please. So this is simply to say that the output available, the publicly available output on ESGF is quite large, covers a wide range of variables and most of the experiments and data requests from the CMIP6 endorsed MIPS. And so this wide range of published output variables presents the opportunity for extensive model evaluation, as Michael highlighted. is really something important for us going forward to improve future versions of the model. I already noted a large ensemble is available, and also I'll just note that it's now a standard feature of CAN-ESM that the model can output a CMARized NetCDF following the CMIP6 conventions to facilitate routine comparison of our new versions with existing CMIP models, including our previous one, for example, using the diagnostic package that Michael mentioned, or indeed any community tools. Okay, that's all. Thanks.
Thank you, Michael and James. Do we have any questions or comments? I can see Philip Austin. Yes, Philip, you can unmute yourself.
Yeah, just a comment back to the commercial cloud. So as you may know, there's a separate archive for CMIP6 stored in ZAR format on Google, and a lot of the Canadian data is there. But just to alert people that there's been kind of a technical breakthrough called Kerchunk, which allows you to produce cloud-ready data from NetCDF. So a new way of indexing the NetCDF data set. So you can do multi-threaded reads, and it's object store compatible. And so I think this is kind of a game changer in that you don't have to rewrite all of your NetCDF files into ZAR to get optimized commercial cloud performance. So that's going to really smooth the way to actually move these data sets into the commercial cloud if we wanted to.
Thank you, Philip. Is there any question? Paul, you wanted to say something?
Well, yeah, Michael, just to say in response to your call for collaborations, that's great to hear. And you know, I think part of the reason to have this CP4C is to get CAN-ESM on the radar screen of as many people as possible, and ensure that there are lots of eyes on the model. So I'm not sure how we should coordinate, but it's certainly part of my hope. And it goes back to Vivek's comment as well, that, you know, we treat this as a kind of a national resource that we're all looking at and you know, taking interest in. So I think it's great. You know, if like you have an issue tracker, I think it's a great way to treat it. There are bugs, right? They're emergent bugs kind of thing. So I think I really like that idea. I know they're not all arising from errors necessarily, but it's that kind of spirit of it is really great. So just to say, I don't exactly know what we should do, but I think, you know, maybe making a more formal mechanism for collaboration and ensuring that you always have the resources as new versions become available, and like a lot of interest and so on is a really healthy direction.
Yeah, I agree. And I guess the first step is for us to know who is interested in contributing to specific working groups, or.
But yeah, if there's a list of existing working groups, if you could there's a comment document. So if you could put just what the current working groups are, you don't have to say to put down too much, but just like a list, and we can make that part of the minutes of the meeting. So that would be a great start.
Yep, sounds good.
Yeah. Yes. And do you, from your past meetings, is there any record of those past meetings, like in terms of presentations or summary or anything like that?
There is, but the problem is that it's all on GitLab.science. but so the GitLab.science is only available, is accessible to is internally. Okay. So we have been considering to make this more public and move it over to gitlab.com, but yeah, it's a bit of a hassle. But if there's interest of the outside community to contribute this, it may be worth doing that.
Yeah, let's. I don't know, but I think it's worth exploring. So thanks.
Thank you, James. Do you want to add something? I can see your hand raised.
Yeah, me? Yeah.
Yes,
Yeah,
Eddie.
yeah. I just wanted to mention. I recall the Met Office. I wonder if this might be one possible model for going forward with collaboration with the academic community. The Met Office, I recall, has these things called process evaluation groups, or PEGs, where they'll have a bunch of people might meet to discuss, say, I don't know, blocking storm tracks or something, and they meet every 3 months or something. So currently, our working groups, as Michael described, have been an internal thing where people report progress on in these regular A4D meetings we hold. But I guess that's another possible model, some sort of small independent group that meets on their own and perhaps every so often at a longer time interval brings feedback to the modelers. I don't know, just a suggestion. I don't know what other centers have done, like NCAR, for example.
Thank you, James. Okay, so following our agenda, our next speaker is Jason Cole from CCC, who will talk about the CAN-EM development.
Okay, I'm going to turn off my video for bandwidth, and I'm going to try to share my presentation somehow. So share screen.
Sure.
Share. Okay, can you see this presentation? And then I'll try full screen.
Yes, we can see it.
Okay. Is there stuff on top of it, or is it?
No, in a presentation mode. Looks good.
Okay, all right. So I'll just go ahead then.
Yes.
Okay, so yeah, so I'm going to talk today a bit about the CAN-EM, so the atmospheric component of CAN-ESM, and just kind of give a high-level description of what we've been working on, what we plan to work on, and some of the research interests that are kind of related to CAN-EM that might be of interest to the larger group. And I'm giving the presentation, but this is on behalf of the larger CAN-EM atmospheric physics working group. So just to put it in big picture kind of thing, so we're kind of trying to do all the atmospheric processes in CAN-ESM, like I said. We have some pretty big components that we have physical parameterizations for, so gravity waves, convection, aerosol, clouds, radiation, boundary layer, and chemistry. One thing I'll note about CAN-EM is that a lot of these parameterizations are in-house parameterizations. So these have been things that have been developed either at CCMA or in collaboration with Environment Canada or sometimes academic collaborators. So it's a little bit of a unique model that we don't have components that we've taken from somewhere else, like say the radiation. We don't have a radiation code from our RTMG that's put into our model. We have an in-house radiation code, which is, I think, kind of interesting. So on the right-hand side, it's just a list of who I would say at CCMA are kind of the core people in the CAN-EM working group. So it's not a huge number of people. We have our own expertise in different parameterizations. I'll note 2 people on that list are newly retired or really retired, but they still contribute to developments. Surprisingly, those of you that know Norm McFarland, he retired, I think, quite a while ago, I think even before I started at CCMA, but he still is contributing to our model developments. So I'll just kind of give a quick overview of some really recent work we've done on improving or developing our CAN-EM physical parameterizations. So one thing that's happened a lot in the last year is Jingnan Li, who has developed the radiation code, has spent quite a bit of time updating the code. So he's done a real revamp and a real bringing up using all the new spectroscopy to update its correlated K distribution model. That's for gases absorption. He's also been looking at aerosol optics, improving those. As you may well know, for radio transfer, there is the radio transfer solvers. So up till recently, we were using only 2-stream solvers. But Jingnan has also added in the last couple of years the ability to actually have a very efficient 4-stream solvers that we can use. And this is a very nice move forward in radio transfer models. One thing that I've added for participation in CMIP6 was the ability to actually have like a driver enabling us to run sorry, hope that didn't pop up, run the radio transfer in like a single column mode offline. So you don't have to run it interactively, but you can actually run it, the exact code that we use in CanEM on single column applications. And this is quite useful for different applications. Another thing that's being developed and currently going on is developments and testing of a new deep convective scheme that was largely developed by Norm McFarlane. We also have a boundary layer scheme that is currently in CanEM as an option that we're evaluating and testing and looking at it very closely. Another thing that we added as part of our work towards CMIP6 is the Canadian Small Lakes model, which is now incorporated into our CanEM. And I'll just note that these are currently physics that can be turned on and off. So we've kind of gone to the approach that we have our current core codes, and then we're kind of in the process of testing and evaluating. So we have the ability to switch on these new physics and test them as we see fit. And then eventually when we feel that they're ready for prime time, we will make them the default option in the model so that it will be the full tested physics package that we expect to use. It sounds like John talked about his methodology that he's been testing for parameter adjustments using objective methods, which has shown to be quite powerful for setting uncertain parameters in these parameterizations. So in addition to the, those things I just talked about, there's also been a lot of work recently in aerosol and chemistry. So as many of you might know, we have a very long history of middle atmosphere chemistry modeling. It's particularly related to stratospheric ozone. There is some tropospheric chemistry, but it's using quite simple mechanisms. So there has been an effort over the last year or 2 years to actually pull in the gas phase chemistry from CMAM, the Canadian Middle Atmosphere model, which is on quite an old version of the GCM, and bring it into the most latest version of CanEM. So that's ongoing. I think it's progressing quite nicely. Another thing that has a lot of work done on it is upgrading our aerosol microphysical scheme. So by default, we have what's called the bulk aerosol scheme. This is what we've used for CMIP6 and continue to use by default. But we've recently been able to pull in Knut von Seltzen's PAM aerosol microphysical scheme. And currently it's encoded into the model as an option, but you're able just to flip a switch and use that other aerosol scheme to do particular applications that you want to use it for. And of course, we're constantly testing and evaluating it. And in the model, we have aerosols that don't live on their own. They actually interact with other components. In particular, they interact with the radiation to get the direct effects. And then in the clouds, we get the first and second indirect effect coupling. And then, of course, as they fall out, one of the big effects is if black carbon falls on snow, it changes the snow albedo. So these are impacts that we've encoded into the model related to aerosols. And as noted below on the last 2 points here, there has been some testing done where it's seen that CanEM 5 with PAM turned on performs quite well in the Arctics, based off some work that was contributed to the AMAP model in comparison. And there's some broader uses of PAM as well, this new aerosol scheme where it's being coupled to look at climate aerosol connections, not only in our model, but also with the GEMMAC model and other government groups. So in addition to all the effort being put onto the parameterizations and the physics and chemistry and aerosols that are in the model, there's been quite a bit of work in the last couple of years to actually do some very necessary and very important technical work for CanEM. So one thing that we're working on right now, and John might have touched on it in the CAN RCM discussion, is that we have the capability now to actually run the CanEM physics, not only in our spectral dynamical core, but also in the GEM dynamical core. And this is in limited area mode for the RCM, but also as our global atmospheric model. So of course it's needed for the CAN RCM, and we're currently in the process of evaluating and configuring what we call CanEM GEM, so CanEM with the GEM dynamical core. And it has a lot of nice benefits. It seems to be fairly efficient, particularly for certain applications. And one thing that's of interest to us for atmospheric physics development, it has a capability of being run in single column mode, which is quite attractive. Because as many of you might know, when you're working on physical parameterizations, that's quite a nice way to do some initial development work. And then into the actual core codes, there's been a lot of work trying to modernize our CAN-EM codes. This is to make the code more robust, easier to use and maintain going forward. And this has been a lot of work that's been led by our technical group to help guide some of this effort to use more modern Fortran and software practices. For example, clean interfaces to connect physical parameterizations with the main code. This idea of using switches to have optional physics during testing, so it's easy to flip things on and off while you're trying to look at things. Something we did recently that was quite big was we were using fixed formatted Fortran 77 for all our code. That was getting a little bit difficult to deal with, so there was a full recoding of all the physics codes to use Fortran 90, so free line formats. And those of you who know Fortran, there's this implicit none. So every variable has to be explicitly defined now, which can help, again, with the idea of making it easier to work with and maintain. A project that we have going on in parallel, just kind of constantly going along, is trying to improve our documentation. So this is quite useful when internally for us, but also when we try to collaborate with others, to have both inline comments in the code and also trying to utilize the so-called Doxygen way of putting in information so that people can quickly understand what's going on in the particular physics routines that are in the code. And on the bottom here, I just have an example from that John Sunoka added for his gravity wave drake parameterization, where this documentation that you see at the bottom is automatically generated by Doxygen based off information that John has added in line with his code. So it can be quite useful if you're trying to look at particular parameterizations. So just to give you a sample of some of our future developments and needs. So on the top, I have in the box just kind of, I guess, where we've kind of seen as a roadmap, or my hope personally, where we might go over the next near term and midterm, is to kind of have a version of CAN-EM that is capable of modeling the atmosphere processes, including aerosol and chemistry, from the surface to the stratosphere. So that doesn't mean you'd always work with that kind of configuration, but you have the capability of configuring the model to that full extent, or any kind of application specific in between. So I mentioned before some of the parameterizations that we're working on, we have been working on and continue to work on. There are a couple of things that we are currently starting up and kind of gearing ourselves up, or might feel that's necessary going forward. One thing that we recently started looking at is basically upgrading or improving our cloud parameterization scheme. So the one that we currently have, it works well, but it's not state of the art. So we are working with colleagues within Environment Canada to use the so-called P3 cloud scheme, which is was developed in the NWP group and has been expanded to lower resolution models. And we're starting with that. Of course, there's going to be a lot of work about trying to couple it with our aerosol radiation schemes, but that's something we're starting to take on now. So historically, we've been quite strong using this middle atmosphere configurations of our model. It kind of went down a little bit given the resource limitations, but we kind of want to start bringing that up a bit more. So having a middle atmosphere configuration of CAN-EM spectral and the CAN-EM GEM versions of the model. And one thing to help do that is the so-called rate of transfer in the non-LTE region. The one that we have has some limitations, but from what I understand and what we're going to do in the near future is bring in a community version that should be more working in more broad cases. Of course, we're going to couple with Classic, which maybe we talked about. And then there's a few other things related to aerosols and chemistry. So interactive wildfires, considering nitrate and ammonium aerosols, which are quite important, VOC chemistry, and looking at improving dry deposition for both gases and aerosols. These are all processes that are important going forward. And then, of course, model development on its own is quite interesting. It's fun to do, and it's required, but of course you want to think about the kind of applications and research that you want to do with the model once you have something that's ready and available to use. So as Michael just said about the A4D group, we would really benefit from a lot of model evaluation and usage using CANI-M in a wide range of applications. And that could be existing, and hopefully we have a collaborative version of the model for bespoke experiments that people can work at and use and run that could really look at things in a different way. Personally, one thing that I'm interested in is climate intervention or geoengineering, as you might have heard about. That is a area of research that could be useful, and it's kind of connected to some of the developments we have to do. More broadly, it's also connected to stratospheric aerosols, so volcanic eruptions, wildfires. There's also work related to air pollution and climate interactions, so the impact of wildfire activity, how warming due to deposition of light absorbing particles on snow and ice, and emissions from changing sources occur. There's also broader questions about radiative forcing processes and their impacts on circulation. This could be related to changes in the air pollutants and things like that, and looking at different strategies. And that also, on the flip side, could also be related to climate intervention. If you put intentional radiative forcing changes in a certain region, how does that impact circulation and climate as a whole? And also, I put on the bottom here, it's kind of an up and coming thing, but the thinking about what the potential role of machine learning and AI might be in atmospheric physics and research and development. It's kind of an open question. And with that, I will stop. Thank you.
Thank you, Jason. I can see one question from Neil in our shared file. I don't know, Neil, if you want to speak for that, or do you want me to read it for you?
It doesn't need to take up time here, just if Jason's able to reply to that. I was actually curious about who the atmospheric chemistry, tropospheric chemistry experts were in your working group, because I've got a student working on modeling of tropospheric chemistry related to CESM, and I think there's potential for input from Environment Canada folks there. So if there's
so the lead person on our chemistry is Dave Plummer. Okay. He is the one that developed the stratospheric aerosols. I mean, I don't know if Knut's online, might be able to say a few words, but yeah, there's a core group of people that work on short-lived climate forcings and chemistry interactions, as well as aerosol. But yeah, I think if you get in contact with Dave, that might be a starting point.
Yeah, sounds good. That's actually who I was thinking of. So yeah, good to get that confirmation. Thank you.
Thank you, Neil. Philip, you want to mute yourself?
Yeah, Jason, just two really quick in the weeds questions. So now can you run with bounds checking turned on for the model?
We are getting much closer. Yeah, I think getting even farther into the weeds. I actually tried to run the radiation through Valgrind, and surprisingly it worked. So it's yeah, I think we're getting closer and closer to be able to really check the code.
And are you working with a compiler that would be free for us, or are you tied to a paying license version, or what actually works?
So Neil might make a comment. I know for the offline radiation code, I can use it on G4chan. It's no problem. I think Neil, you've compiled it on different. Yep. I think G4chan.
For the full CANI-SM, we compile it with GNU in the container. But yeah, I can compile it with GNU on my laptop, no problem. And yeah, and then on Compute Canada, we also use the Intel providers that compilers that they provide. So yeah, Intel or GNU are what the support compilers are right now.
Thank you, Philip, for your questions. I cannot see more questions. Anyone?
Well, I guess I'll kind of bang the same drum, but just to say, you have a small group to undertaking a huge number of problems, and this just seems like there are lots of opportunities for collaboration, and it's a question about how to organize that. But those of us, who are doing more work with CSM, like there's no real reason that we shouldn't also consider using CANISM if we can make it as easy to use as possible. So, just to say.
No, it's right. I think we often hear that we're punching above our weight a little bit about the number of people that we have and the amount of work we're trying to do.
Well, there are real efficiencies in doing what you've done. Like you have this core, you have really deep expertise, right? And like Vivek said, as you're adding more and more to the models. And I was also struck by the strong, like as you're getting more into chemistry and wildfire and other Earth system processes, that the need for increased coordination between the classic development and the atmospheric development, it's just going to become more and more pressing. And this might be, and because of that, there's also might be more opportunities to bring in external collaborators.
Yep, I see Knut's name there, but yeah, I think I did advertise some of those. I think Knut's interested in collaboration with if anybody can come in and want to be involved. You can contact Knut.
Yeah, for sure. Yeah. Okay.
Thank you, Paul, Jason. Now I welcome Jack One and Paul Kushner, who will be talking about the CAN-AM parallel sequence performance on Compute Canada platforms. So Jack, let me know if you can share your screen.
Yes, let me share my screen. Can you see my screen now?
Yes, we can see it.
So hello everyone. So today I'm going to present CAN-ESM porting and performance on Compute Canada, or the Alliance platform. So I'm Jack Wong from University of Toronto, and this work is supervised by Professor Paul Kushner and also Neil Swart. So an introduction. I'm a third-year PhD student in civil engineering with a research focus on the impact of climate change on tall buildings. So before my works in CP4C, ported version of CAN-ESM was containerized, but this limited flexibility for performance optimizations. As part of the CP4C initiatives in 2022, tools were developed to build CAN-ESM with MC and bare metal from scratch. This was described by Neil previously. In the CP4C group, I'm tasked with testing and optimization of the CP4C implementation, basically to find the optimal settings for best throughput and also efficient use of resources. So let me introduce a little bit on the bare metal pod and MC, which is a big achievement in CP4C. So for the bare metal pod, which means now on the Compute Canada platform, the CAN-ESM is compiled from scratch using the native Intel compiler and libraries on the supercomputer Niagara, as compared to previously we had it in the container. So with the bare metal pod, it's simpler to detail with the runtime details and to ask for support on the bare metal version, because we don't need to go through the container to get this information. And then for the MC, which stands for Integrated Modeling System Infrastructure, it was developed and designed to manage the complex configuration of platform, machine models, experiments, and parameters of the simulations. It's a generic set of Python-based parsing routines and utility functions with a command line interface. It has a goal of being easy and logical to use, logical and accessible information management, and traceable flow. It's robust, portable, extendable, maintainable. So later I will show how I use MC easily to do my optimization. And this MC is currently stored in Neil's Git repository with ongoing development. With MC instructions to build and run bare metal pods of CAN ESM can be stored in a Git repository and share across user, so to make it easy to use. So my first experience with CAN ESM, previously I have not run any climate simulation before, but only some computational fluid dynamics simulations for my research. So my initial task, my first task was to do the initial testing on the bare metal pods and MC implementation of CAN ESM on Niagara as a user with no prior experience of running climate models. So I just follow the instruction on this GitLab Neil wrote, and just some commands. And the code was built successfully with the predefined setting, and the simulation just ran successfully without issue. As a user, I found it very easy to build the code and run CAN ESM simulation with the default setting provided by MC. And with MC, the default settings are wrapped up in JSON files. So for my optimization, I need to change the number of processors, and I just update this JSON file, and the simulation will just compile and ran successfully, so which is very easy to use. And then, so after initial testing, my task was to find optimal settings on Niagara. There are few main variables. So for the CAN AM process, there is the number of MPI processes and the number of thread allowed for open MP thread allowed. And then for Limo, there's the number of MPI processes. And finally, how these processes are distributed across the node. So for the optimization, I used this experiment, which is one of the default setting, and then for this model. And the simulation starts from year 1000. And the criteria would be the throughput, which is measured in simulated year per day, and also for efficiency measured in CPU hours per simulated year. So there has been some steps to do the optimization. I will go through them later, but this is some of the final results of the selected optimal settings. So there are 3 settings. The first number is the number of nodes. In Niagara, the cores are grouped in a group of 40 in one node. So the first number is a number of nodes for CAN AM tasks. The second number is the number of open MP thread allowed, and then the third number is the number of nodes for NEMO task. So I have 3 different configurations here, and the left graph shows the throughput, and then the right hand side shows the efficiency. So I have this 225 configuration being the fastest simulations, and then this 112 configuration being the most efficient configurations. And here show the histogram of these runs. So as you can see, I achieved this configuration as if simulated years of 18 per day, 18 simulated years per day. And then the efficient algorithm has a CPU takes around 300 CPU hours per simulated year. And this distribution has a very narrow spread, which means basically the effect of different configuration would is larger than the spread, which means the optimization is good indicator of the optimizations. And here is a summary of the optimal settings. So throughput is 225 using 32 CAN AM processors distributed across 2 nodes with 2 open MP thread, and 200 processors distributed across 5 nodes on Niagara. And the efficient ones is using 32 distributed on 1 node, and using 80 cores for NeMo distributed across 2 nodes. As a reference, CAN ESM5 on ECCC compute resources has bad performance of 20 simulated year per day and also 325 compute hours per simulated year. So these numbers are quite close when we compare the performance and also this efficiency, which is good thing on Agora. So in order to arrive these conclusions, there were lots of tests being done. So I'll just quickly go through them here. So the first test is to basically parametric study on CAN NeMo MPI processes, basically keeping other as constant and changing one variable for each case. So here we obtain 160 NeMo MPI processes as the fastest case, although efficiency is going lower as we increase that number. And then I changed the number of processes on CAN AM and identify that after the MPI processes exceed 16 on Agora, basically it reads flat. And after that, I try to change the number of open MP thread for CAN AM, but initial testing did not show any performance difference when changing this number. And we basically try to debug and find out what happened. And so basically this CAN ESM consists of 3 MPI programs, and CAN AM use OpenMP, which requires CPUs not binded to MPI processes. So on other HPC system, we usually use the following request to request for the ideal settings. But on Agora, because the resources are grouped by nodes of 40 cores, so this request is not supported by the scheduler. So what happened is all the processes are clustered together, leaving basically no idle or unbinded CPU for CAN AM. So in order to correct that, basically I did quite some trial and error work and found a solution using explicit MD resource distribution through the use of host file. So I wrote a script to accommodate for the configurations and submitted a merge request to the MC repository, which is which illustrates a good thing of putting this in Git repository. So we can contribute to that Git. And after that, this shows the effect of doing this explicit task distributions. This orange point is after implementing the new change. So for this point, if I just distribute this idle CPU to here, then there's some increase in performance. And after that, I tried a more CAN AM node. And with 2 CAN AM nodes, the performance increased dramatically from here to here. And after that, I also tried to increase more nodes when the CAN AM reached a bottleneck. So previously we had 4 nodes for CAN NeMo. And so some work shows that by increasing it to 5, the performance increased. And finally, I did some fine tuning on the efficient case. Basically to distribute, previously we had those idle cores at the last node. By bringing it to the first node, there's some increase in the efficiency and also in the performance. And this is the initial test one. And after all the testing updates, we are getting this sweet spot for sweet configuration to run the simulation on Agora. So quick summary, MC is very easy to use. The optimal setting on Agora have been identified using runs prepared by MC. The new bare metal pod shows good performance on Agora. And also CP4C is under active development and everyone can contribute through Git if you're interested. And some future work, the Jupyter notebook used for this analysis will be shared on the Git repository. And also this will allow the framework to collect, to do queue time statistic on the cloud allocations. and also to perform similar analysis on other HPCs, such as CEDAR and Grantham. And finally, there is an ongoing MC development from Neil. There will be updates on the sequencing tool to facilitate the processing of data, such as diagnostic, archiving, and purging to support production ones. So that's the end of my presentation. Thank you. Any question?
Thank you, Jack. I cannot see any in our share file. Does someone have any question?
Sorry, I couldn't find the raise hand, but can I ask a quick question?
Yes, sure, Jason.
Yeah, so Jack, I'm assuming this is, maybe I missed it, but is this all coupled? I'm just curious if you've run simulations with only the atmospheric CAN-AM alone, because that's something that people might want to do. I'm just curious the throughput on that, or if you've looked at it, or if it's possible.
So currently with this MC, because it has a wrap to run this CAN-ESM model is MC submit. So currently is it runs the whole CAN-ESM together.
Okay, all right, I missed that.
Support just CAN-AM, but maybe now can support that.
Yeah, I mean, yeah, we can easily just run CAN-AM simulations.
Okay, no, I'm just wondering on the throughput on that. Just
I mean, I think the indication is that basically, like Jack solved this technical problem, and so the CAN-AM performance is more or less similar to what we have internally. So yeah,
okay.
Like the coupled model is more or less limited by the CAN-AM performance now.
Yeah. Okay.
So it's like 20 years or 18 years a day. So.
Okay, all right.
Anyone else? And if not, I cannot see any question. So maybe we can continue with our agenda. Our next presentation is about ensemble consistency test. Haruki Hirasawa will present us. So Haruki, let me know if you can share your screen.
Okay, I'm gonna give it a shot. Yeah, okay. Okay, can you see this?
Yes.
Okay, yeah, so great. So today I'll be discussing some work that we have been doing implementing what's called the ensemble consistency test on CAN-ESM in order to verify ports to these new machines outside of the Environment Canada environments. Right. So yeah, this problem of verifying Earth system model codes, code changes and ports is being extensively worked on by I assume pretty much every modeling center has their own approach to this. And the issue is that our Earth system models are complex and they model a chaotic system. So relatively small changes to the code, compiler, processor, they can easily influence the output of the model. And so what we want to do is ask, okay, if we make a change, such as porting a model to a new machine, how do we ensure that the ESM port is performing as we expect in terms of the climate, for example? So here I'm showing three examples of methods for verifying ESMs. There's obviously more than this, but I think these are three pretty standard ones. The first is bit-for-bit reproduction, cheap, effective, and it's usually too stringent for most applications. The second is, I think, what's commonly used at ECCC, which is just running a single long test simulation, which of course is quite reliable, but pretty costly. And then the third, which is I'm introducing here, is what's called the ensemble consistency test, which is cheaper but has a potentially higher false positive rate. That is to say, it sometimes rejects, erroneously rejects ports. So yeah, just to discuss these in a little bit more detail. So bit for bit reproduction is pretty straightforward. You just directly compare test outputs to a reference bit for bit. And the issue with this is, of course, that small changes can break bit for bit reproduction. And in particular, porting ESMs seems to pretty much always break bit for bit reproduction. And so I think perhaps the most reliable method for verifying ports is therefore to run long climatological simulations and then compare the climate mean and variability across a couple select variables, and in order to ensure there's no significant change in the ESM climate. But of course, this requires a fairly long simulation in order to get in order to be confident that the ESM climate hasn't changed. And so the method that was developed for the community Earth system model by Baker et al. In 2015, and they've iterated on this in a couple subsequent papers, is called ensemble consistency testing. And so in short, what this does is it replaces the one single long simulation with an ensemble of short simulations, and then which are then compared against a large ensemble of reference data from a trusted machine. And so this is much cheaper than a long test simulation, but as I said before, it has a relatively high false positive or false fail rate, as I'll show. Yeah, so in the case of CSM2, this is implemented like they provide a nice script that sets up and runs a 3-member ensemble. In their case, they're using 9 time-step simulations. And then you take the data from these ensemble members and you upload it to the UCAR website, and they run the test and tell you if your port is verifies or if it passes the test. And so, yeah, the nice thing is that we can just grab the scripts from NCAR and with relatively little modification, apply them to CAN-ESM5 data. So here is sort of like a outline of the ECT method. So the first two are sort of setting up the reference ensemble. So we start on a trusted machine that's verified, and we generate a very large ensemble of, in our case, 1-year simulations. And then using that ensemble, we generate what's called an ensemble summary file, which contains information about the statistics of the ensemble. And then this is sort of what we use to run the test. And then on a new machine or maybe a new version of the code, we then run a test ensemble, which is a small 3-member ensemble of 1-year simulations. And we sort of compare those against the statistics in the ensemble summary file, and that's the ECT. Right, so in order to generate the ensemble summary file, we first need an n-member ensemble, and notably, this needs to be greater than the number of variables, and also we need a large number of variables, preferably. So as many as possible, and as many as possible for these 2 numbers. And then we calculate the global and annual averages for all the variables and ensemble members. Then we standardize these by removing the ensemble average and dividing by the standard deviation. And then we apply principal component analysis to the standardized values across the ensemble to capture the relationships between the variables in the for the 1-year simulations. Right, so for our case, what we did was generate the reference ensemble on the WestGrid Cedar machine. And so what we were using is an earlier containerized version of the KNESM5 port, not the IMSI bare metal version that Jack was describing. And so Neil ported it to CEDAR and ran a long test climatological simulation, and said, okay, this is verified on CEDAR. And so I then ran a large 250 member ensemble and was able to get 127 variables from that to generate the reference ensemble. And so I guess one thing to notice that we're only able to use 2D variables for now because of that's what's available from the diagnostics. And so these two plots just show some statistics from the ensemble in terms of the principal component analysis. So you see that, at about 50 PCs, we're explaining pretty much all of the variability or variance. And then you see here essentially what it looks like when you look at the individual ensemble members. There's noise because of internal variability. And the idea is that we want to test to see if if we run some new simulations, if they exceed this 2 sigma level of the variance in the ensemble. Okay, so when we move to a new machine and we want to verify it, what we do is we run a small ensemble of 3 simulations, and then again calculate the global and annual mean, standardize it, and then calculate the scores using the PCA loadings from the reference ensemble. And then we run the test. And so there's essentially 3 steps. So first, you go through all the principal components, and then for each run, for each principal component, you check if the PC score falls outside of the 2 sigma range for the run. And then if that's right, and then if that's and so if more than 2 of the 3 runs fail, or sorry, more than two or more runs fail, then we say that the principal component fails. And then if more than 3 of the principal components fail in this way, then we say that the test overall fails. And so this is what it looks like in practice. So it just runs through all of, in our case, 50 principal components, and this one happens to have passed. You see that some PCs fail because of the noise in the ensemble, but few enough fail that we can say, okay, these 3 ensemble members are consistent with the reference. Right. So we conducted the test for port to Niagara. So again, using the containerized version, we just set it up on Niagara and ran a bunch of test simulations. And then we ran 10 member ensembles, and if we randomly resample 3 members from them and keep running the ECT, what we find is that the ECT produces about a false positive rate of about 5%. And so this is true on both CEDAR and Niagara. And so this is probably because of the non-Gaussian distributions at higher order principal components. But you can see if you compare the distribution of the test ensembles between in these 2 panels, as well as the ECT pass rate, it seems like there's similar performance between Niagara and CEDAR, which indicates that the Niagara port passes the ensemble consistency test. So good news. Right, but this false positive rate is higher than we really would like. The ECT is sort of formulated to achieve a false positive rate of 0.5%. And so one thing we could do is just keep increasing the ensemble size. So here I'm showing a plot of the ensemble size versus the pass rate. And so, we're approaching that 0.5% target, but it's quite slow. So I don't know if you fit this, maybe you find we need 300-400 ensemble members. And maybe that's just the solution. We should just do that. Or another method might be to use a different multiple significance test. So for example, I tested the false discovery rate, which is just a method for doing multiple significance testing in order to limit the amount of false rejections of the null hypothesis. And so I won't go into too much detail on this, but I'll just show that if we perform the same analysis but replace the ECT with the false discovery rate, this does seem to reduce the false fail rate or false positive rate for the two ensembles, or at least it doesn't degrade it. And so at least it appears that the FDR is more lenient than the ECT. But I guess in order to get a better idea of the ECT performance, as well as the FDR performance, I think the best thing to do is to push it, change the model until we see it fail pretty consistently. And so what we did was we took the CEDAR installation and increased the solar constant, which is a pretty simple parameter change. And so here I'm showing the principal components for the no perturbation case on the left, and on the right, I'm showing the case where we have a 5 watt per meter squared increase in solar constant, which corresponds to 1.25 watts per meter squared of forcing. And so you can see a lot of the PC in the test ensemble are starting to pop up more out over this 2 sigma of the reference ensemble. And so if we vary the solar constant perturbation and check how strong we need to make it in order to get the test to start failing, we see that for this plot, we have the solar constant change versus the fail rate, or the pass rate, sorry. I've mislabeled this. And you can see that actually, oh no. Yeah, no, this is actually correct. Yeah, so you can see that actually the ECT is not actually failing these new simulations very frequently, even when we're up to like 0.5 watts per meter squared of forcing, which is pretty substantial. That's like, I don't know, about the same magnitude as like the aerosol forcing. The FDR test is actually doing a better job here, where it's detecting the change in the climatology at a higher rate, at lower solar constant changes. So perhaps this is a more reliable way of detecting deviations from the reference. Great. Okay, so just to conclude, we've been able to use the PY-CECT, which was developed for CSM, and we found it can be pretty easily modified to work with CANISM5 data, which is good. And so it appears that the ECT has more false positives for CANISM5 than CSM1. This might be because we only have 2D data. Maybe CANISM is just in some way noisier than CSM1. We also see that the ECT is relatively insensitive to solar constant changes up to 1 watt per meter squared of forcing. So this is a little bit concerning. We would like it to be able to detect that kind of forcing. And the sensitivity is improved if we use the false detection rate instead. So maybe that is a good alternative. Yeah, and just, so yeah, in the future, we'd like to be able to test this for the bare metal CANISM5 port and implement it for the IMSI diagnostic outputs. Yeah, so if anyone has any questions, I'll be happy to take them.
Thank you, Haruki. I can see Philip has his hand raised. Philip,
yeah. So that's really nice. So have you pinged the EC2 developers about the sensitivity? Have they commented on what they think about it, because it seems kind of an obvious test to try and break the statistical metric.
Yeah, I mean, in their paper, I haven't talked to them. I told that I communicated with them early on about getting the ECT set up, but yeah, I definitely should feed back to them about how it's performing with the solar constant changes. I think they had probably better luck in terms of getting a better performance. They had their own set of parameter tests that they did, and it seems like the ECT did a pretty good job of detecting those, but so yeah, I don't know if it's a ECT thing or a CANI-SM thing. Yeah, but yeah, it's true. I should definitely feed back to them.
Thank you, Philip. I can see John Tinoka has his hand raised. John?
Yeah, thanks very much, Haruki. That was an excellent talk. I think this is a perfect example of the sort of a benefit that we get from this sort of collaboration. This sort of test would be hugely useful for model optimization. When you get more aggressive optimization, there's always a concern that they've moved some blocks of code around in a way that changes the physical answer. And so that could be a very useful tool. In terms of your lack of sensitivity to the top of the atmosphere, I wonder if you just increase the length of your runs to 2 years or 3, because I know for a fact, had we run a 10-year run, 0.5 at the top of the atmosphere, you'd see the drift, you could eyeball it, right? And so that's a potential limitation, but it's just a sensitivity, right? You change the number of ensemble members, it's just as costly to make the runs twice as long as to increase them by a factor of 2. And I think in this instance, it would pick that up quite much more quickly, because it's just the ratio of that internal variability to the ability to pick out that signal, which is one thing. Another thing I was thinking too is if you started from an initial state that was a constrained initial state, so we play around with this nudging to sort of constrain the model to follow observations. Of course, if you let it go, it drifts back to its state. And that's a big signal. And I'm wondering if we also thought about starting with an initial state that was something that would provide a larger signal of the model trying to go somewhere, that it might also help you. I mean, so there might be like a little ensemble of tests that you could do that could sort of pick out things rather than just sticking with one set test and increasing ensemble numbers. But just really, I mean, just get you thinking, seeing this really, really interesting and potentially very useful for us.
Yeah, thank you. Yeah, I think it's definitely an adaptable method. I think you could definitely take it in any number of directions in terms of trying to improve the performance of the test. I'd be happy. Yeah, like, I mean, in the case of the CSM, like they claim that you don't even need, like 1 year is even a lot. You can do it with 9 time steps. So I think the way they see it is that really it's like, because you're able to compare with the same initial conditions, it's really like if it is different, it tends to diverge, even at relatively small time scales. But
yeah, I mean, this thing of using a small number of time steps, we tried it in the past because George Bohr had come up with this idea that the kind of spread in an ensemble theoretically what it should be. And our initial attempts were thwarted. I bring this up that the land surface scheme had logic in it that would jump the response orders of magnitude because it wasn't continuous across its input. And if you get anything inside your model that is not coded in that way, that has sort of different cases that it has with conditionals, it isn't continuous, you can pump a lot of noise in there and really undermine that sort of spread. And it may be that we have something in there that makes that much noisier, say, than another model that prevents us from seeing it, and it artificially inflates the noise, which seems to be what you found.
Thank you, John. I can see Neil has his hand raised. Neil?
Yeah, already nice. Thanks for the talk. I guess, yeah, just 2 quick questions. The one was, I believe for CSM, they're using quite a big ensemble, like about 400 members. So maybe like, close to double what you're using. Is that correct?
I believe they use 250 as well.
Oh, 250. Okay.
Yeah. So yeah, your guess is as good as mine as to why the performance is different.
Okay. And then my other question was just about this FDR. Is that something that they're thinking of making available as a separate test, or is this just something that you've been exploring kind of on your own?
This is just something I've been thinking about on my own. Like I started using this for my doing field significance tests with precipitation fields, and I sort of realized that there's a lot of cases where you're doing many tests together, and this is one of them.
Yeah, well, I mean, that's awesome. So I mean, not only could this be super useful for us, like the whole general applying it to CANI-SM, but kind of following up on Phil's comment, maybe they would even be interested to take back like an alternative test, or if it shows an improved performance. So yeah, all around really nice. Thanks.
Thank you, Neil. I cannot see more questions in our shareholder nor in our room, so maybe following our agenda, maybe we can take 5 minutes break to stretch our legs and grab some water, and then maybe we can reconvene again just to hear reflections and some discussion. Yeah, Paul?
Yeah, just could I ask Neil and Danielle, if we could just meet quickly in a breakout. I just created a breakout room, and if I could just pop us there just to have a couple minutes to talk about like the last little bit, and then I'll promise I'll let you go. Okay, is that okay, Neil? I'll just move us to a breakout room.
Yes, so everyone can take a break.
Everybody else can take a break. I promise not to take a long time. Neil and
Great. I think it is time. So thank you, everyone. I hope you had enough time to grab a glass of water and stretch your legs. So I will invite Paul to start the discussion, final discussion of this day.
Yes, so this is not the end of the workshop, it's the end of day one. And I didn't want to take up too much time today. I definitely would like to end by 4:30. I was listening to the talks. I really appreciate everyone's presentations. I think there's a lot of great information that we can summarize through our notes, and even a couple of questions that came up in the Google Doc as well, which you can feel free to contribute to. I think the overwhelming impression I had was of just how productive and busy everybody has been in working so hard on CANI-SM, inside CCCMA. And I'm really happy to see the beginnings of a contribution, from CP4C outside of CCCMA as well, right? Historically, CCCMA has had relatively small teams of people working closely together with very, very deep expertise. It just does seem to me, though, as that the climate modeling enterprise is getting bigger and bigger, that there are more and more tasks than a small team can handle, and that the time is ripe for really coming up with mechanisms to enhance collaboration. I won't have anything magic to say today about what those mechanisms will look like exactly, but I feel that CP4C, this idea, is a good part of that, and as we shape it together, if we plan it collaboratively, it will work as a really effective tool. Particularly, one of the things I did notice were projects that are growing in scope, such as A4D. That if a list of desired diagnostics or goals for that effort were written down somewhere, there might be a group of people outside of CCCMA or outside your current network that could actually jump in. So documentation is important. I think that's one thing. So that's not at all critique of what you've done so far, but it sounds like the time might be right to explore that a little bit more. We had a couple of comments as well from Phil on the cloud capacity and really taking advantage of cloud technology to do more analysis of CANI-SM, but also CANI-SM in the context of the CMIP, the larger CMIP effort. So I wanted to stress again that and Phil wouldn't know this, I don't think, but part of our effort in the CP4C proposal to Compute Canada was to obtain cloud resources, partly to prototype that kind of activity. That if we could have some guaranteed resources to do some prototyping, some analysis, that could then translate into something larger later on. So that the resources exist, and I think ideas, when we have some ideas that are in the proposal, but we could definitely exploit more. And I guess overwhelmingly is that the main takeaway is that I see a lot of people inside CCCMA who are willing to collaborate. Resources are an issue. Time is an issue, is maybe the main issue, and so coming up with ways of identifying priorities and using everybody's time. I hate wasting people's time. So using everybody's time effectively, that's kind of the priority. When we were just before the break, Neil and Danielle and I were also talking about a couple of other things. I think, Neil, you were going to say something about like the regional modeling effort and GEM and the sort of where that's going. Maybe I'll pass it to you.
Okay, thanks, Paul. Yeah, so we did briefly touch on this. There were some questions about GEM, but different people in the group were talking about different, like internal CCCMA development. And so I just wanted to mention that on the atmospheric side, so within CAN-AM, although there's testing of CAN-AM5 physics and GEM, both for the RCM, so for CAN-RCM5, but then also at the global scale. One of the big challenges, there's two big challenges that I see. The first one is that to get GEM into CANI-SM, we have to couple GEM into the rest of the ESM system, basically through our coupler. That's kind of a major challenge that we don't exactly know how that's going to go. And yeah, there's a host of technical and political issues and all kinds of issues. So it's a challenge, but so that's not available yet, and that's going to take some time to become available. The second issue relating to that is that the current model components that we're kind of offering in collaborative CAN-ESM, we have more or less absolute control over. Even though NEMO we take from the community, but for most of the components we have absolute control over it. For GEM, that's not exactly true. It's an open source model, so but there's challenges around like how easy is it going to be to make that publicly available in terms of like easily compiling it and easily running it elsewhere. So those are things that we do plan to face down the road once we have it working in CAN-ESM. But as I mentioned before, there's just kind of a multi-year effort that will be involved in that, whether we're talking about external people being able to run just an atmospheric model, whereas the global atmosphere or regional atmosphere, or the coupled model with GEM. So yeah, that's just what I wanted to say about the GEM side of things. Thanks.
I don't know if you wanted to add anything, Daniela.
I think both of you have covered everything. I mean, one of the main actions for us is to need to figure out the ways to explore cloud technologies, right? That we can do in our current proposal. Yeah, you mentioned already.
Yeah, and just one other thing, and that is that we haven't talked about observations and the role of Earth observation data in Earth system model evaluation analysis. I think it was striking actually in Vivek and Joe's talk about just the number of data sets that are going to be needed to bring into the models as they become more sophisticated. And there's a bit of a data management challenge, but also a lot of opportunity there to think more carefully within Canada about how we do observational model comparison, and that's sort of an aspect of model validation that be great to have a discussion of sometime. Kaylee Walker is still on the line with us, I think for a little bit longer, maybe not. Gave a talk about that last year in our panel. So that's something still in the air, but it hasn't. We didn't have a lot of time to cover that today. Before we yeah, go ahead. Yeah,
I just wanted to expand on that because I think there's a nice synergy here between talking about making this A4D exercise more collaborative. This wasn't directly discussed in the previous talks, but one part of that A4D exercise that kind of intersects with that objective model tuning that John was talking about, and John could talk to this a lot more, but it's all about coming up with really good observational metrics that you can use in a subjective test. And so you have to have some observational metric, and you also have to have, very importantly, uncertainty on that observational metric. And so I think there's a huge potential with the broader community here, space-based Earth observations or whatever else it is, to help develop the set of metrics. And then people would know every time that a new model version is created, it's going to be tested against this observational metric to see how the tuning fits in with that. So I think there's a really nice way to integrate that, not only just into the analysis, but it will directly feed back, in a sense, to the development.
And Kaylee has a comment on this. So definitely, Neil, it is something I'm thinking about how we can work on this. So great, good. And I'm thinking of Yi Huang was also on earlier, and I think he might have something to say on that very topic. I don't know if Ivy wants to say something, but we have Vivek, and Vivek has his hand up.
Okay, thanks, Neil and Paul. So on the GEM side, and Jason knows this better than anybody else, that we do not have GEM-based CAN-AM yet. We are working towards that, and I do not think CCCMA has the capability to support both spectral dynamics-based CAN-ESM and a GEM-based CAN-ESM. We have to choose one going forward. But until that happens, are you in some kind of limbo, Paul, that you are waiting for GEM-based CAN-ESM, which will take, we're hoping to get it for working for CMIP7. It may not. and Neil and Jason can say more about that. But in the meanwhile, you are trying to run spectral dynamics-based CAN-ESM, and you can do science with that, of course. So is that a problem for you, or can you work around that?
Yeah, I think it's, I think Neil's used this wording, you know, it's where we are and where we aren't, right? I really think there's a lot of scope for work with over the 3-year timescale of the RPP proposal, for example, and the NSERC Alliance Mission proposal was also a 3-year timescale. On a 3-year timescale, you know, that can give us some time to see what kind of community wants to work with the model as it is. But there are lots of models that, you know, as time goes on, their dynamical cores undergo evolution. I would think that there's lots of work to be done on whatever version of the model is actively being used by, you know, used for analysis by CCCMA. As you said, right? You said yourself, right? You said you're so tied down with development, there's hardly any time for analysis. So what we're saying is at a minimum, we can act downstream from what you're doing and help with analysis. But I also think there's lots of perturbations to current models that that lead to very good science and great projects for students as well. That can be where you can take a model as it is, right? I mean, this is a very well vetted and documented model. So I'm not worried. I'm not actually worried about this. I'm actually hoping that the greater the number of eyes on the model, the more interest there'll be in the next versions of the model, right? Maybe it'll help. So yeah.
I just want to add a small thing to that, which is it's not really different for people outside than inside. It's the same conundrum in a sense. And people, it might not be that obvious, but when we talk about this importance of the CAN-AM physics plugging directly into the GEM dynamical core and exactly the same code, like literally line for line, the same code plugging into GEM, that liberates people from having to make any of these decisions. All CAN-AM developers are mostly doing their development in a spectral dynamical core. Any development that you do on the physics in the spectral core just goes into GEM seamlessly. Like there's no like special GEM stuff. It's the physics is one and the same. So actually, it's not like someone would do some development on the spectral dynamical core side and then that would become orphaned. That it wouldn't, because it's the same physics package. So I think that kind of helps to alleviate any concern about that to some degree. But yeah, people won't be able to run 1 degree GEM.
Yeah, I agree. Yeah, hopefully, yeah, it's as Neil said, a physics package that's moved into a different dynamical core, but there's tons of things that internally we're doing the spectral one in parallel. And I just mentioned it because it's something that we're working towards internally, but it's not something that's going to, even internally, it's going to happen right away. It's just, we're doing this parallel effort, but the core physics, it's in both ones. That was a lot of technical work to make that very seamless, that you use one core or the other, and it's quite clear. So I think there's a lot you could do with the spectral model that's available for collaborative work.
Thank you, Jason. Thank you, Neil. Vivek. I can see John Sinoka has his hand raised. Please unmute yourself.
Yep. Thanks. Yeah, just to follow up on the observations. Yeah, they're of critical importance to the tuning, or I call it screening actually, but it's the uncertainty that's the most important, because you don't generally get that with observations or people pulling that out. And what's really required is something for the automatic tuning, the objective tuning is scalar values of things. If you're interested, say, in the QBO, a couple of scalars related to the QBO with uncertainty. If you're interested in mid-continental warm biases in summertime, you form an index for that with an uncertainty associated with it, of those from observations. And what the tuning gives you is a model with parameters that you already know satisfies that metric within OBS uncertainty. The fact is, the more metrics you have, the better of that character, of that quality with the uncertainty. And of course, the model limitations, its structural uncertainty says it can't satisfy all of those at once. But what we can provide is a model, a set of parameters that satisfies this group, and we can tell you beforehand. So you already know that the model satisfies it, and then you can drill down on structural or physical processes. So this connectivity to the A4D is going to become more and more important. And then after the fact, digging much deeper down into the physical processes going on. But yeah, so if we had help in even defining those metrics for things that are of particular interest to people with those associated uncertainties for something like a scalar or an index, it would be very helpful.
Thank you, John. I can see Michael's hand as well. Michael, do you want to add a comment or ask a question?
Yeah, with respect to the seamless swapping in of the spectral versus the GEM core, that's absolutely true. The physics is exactly the same. I don't think it's a showstopper right now, but people should be aware that there is quite a bit of a difference right now in the climate that we are getting between the two. We have not had a lot of time to investigate it on the GEM side, so it may be that we can resolve that quite easily. And if not, I don't think it's going to be a major showstopper for now, but there is that difference that should be noted.
Which isn't surprising, right? That when you make when you change the dynamical core, you will get differences. But hopefully with these newer methods coming in for parameter settings, you have a path forward to sort of objectively tune both, at models as new versions of the model. It's very ambitious, I guess, because you have to do a lot of simulation. But I like John's proposal as well, that of making an effort to identify a core set of metrics, right, that would be of interest, and also the applications in the Canadian setting, right? It might be that we do want to have a bit of focus on cold climate processes, maybe a bit, even though you don't want to you don't want to be completely unbalanced, but it is a good idea, I think, if we're thinking of a lot of regional applications, to make sure that the model biases are at least not egregious in the regions we're most interested in, right? I like that idea, John, and I think there's scope there, lots of scope for collaboration. I mean, I'm sure you're involved internationally as well, but just to say that within this community we're trying to work up here, that could be really a nice direction. Okay. Sorry to keep talking. I don't think you'll hear me as much tomorrow, but I just want to set the stage for tomorrow again. So if you look at the topics tomorrow, the first panel will focus on kind of science and different domains of interest for applications of CAN-ESM. So if you have questions, please contribute them to the document. We'll add a couple of pages for tomorrow's panel soon. It'd be great if those questions came up before the discussion starting at 1 p.m. Eastern. And then the second panel is a bit more about the CP4C itself and how these collaborations might work. And so there's quite a diverse group on the panel from different areas. And so hopefully that'll engender some really good discussion. So are there any other final comments that people would like to make? Okay, well, hearing none, I just like to say again, thank you to all the presenters for a great set of talks. Thanks, Daniela, for running this so well. And yeah, thanks everyone for coming. And I do hope to see everyone tomorrow, and look forward to the discussion then.
Looking forward to see you tomorrow. Bye.
Bye.
Bye. Bye.
Bye.
All right.